You probably think you know where you are. Earth orbits the sun sits in the Milky Way, and that's that. Simple, tidy, mapped out long ago by people with telescopes and mathematics. But here's the thing about the universe. It has a peculiar habit of being far stranger and far larger than our first confident impressions suggest. For centuries, scientists believed they had the Milky Way figured out, a neat spiral galaxy with clear boundaries and predictable structure. Then new eyes began to peer deeper into the cosmic dark, and what they found challenges everything we thought we knew about the scale of our galactic home. Reality, it turns out, has layers that even our best instruments are only beginning to reveal. We'll be exploring this expanding mystery in more depth in this video, and learning how our cosmic address might need a major rewrite. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Picture light traveling at the fastest speed possible in the universe, racing through space at 186,000 miles per second. In the time it takes you to blink once, that light could circle our entire planet 7 times over. Yet even at this incredible speed, it would take 100,000 years for light to travel from one edge of our galaxy to the other. There's something humbling about numbers this fast, something that makes us pause and wonder about our place in this cosmic architecture we call home. The James Webb Space Telescope sits nearly 1 million miles away from Earth, floating at a special point in space where gravity finds perfect balance. It doesn't look like the telescopes we imagine, with their domes and mountaintop observatories. Instead, it operates more like a cosmic heat sensor, detecting infrared light that passes through dust clouds, where visible light cannot go. This ability to see heat signatures in space has opened up regions of our galaxy that remained hidden for centuries. Ancient civilizations looked up at the night sky and saw a pale milky stripe stretched across the darkness. They wove stories around this mysterious band of light, imagining it as a river where spirits traveled, or perhaps a trail left behind by wandering gods. Some cultures believed it was spilled milk from a divine source, which is how our galaxy got its surprisingly gentle name. The idea that this soft glow was actually made up of billions of individual stars wouldn't emerge until the early 20th century. Cosmic dust fills the spaces between stars, but it's nothing like the dust that settles on furniture. These microscopic grains contain carbon, ice, and silicon, drifting through space and creating beautiful nebulae while simultaneously blocking our view. Imagine trying to see through a foggy window at night, and you'll understand the challenge astronomers have faced for decades. This dust absorbs and scatters visible light, turning what should be clear views into mysterious dark patches. The method astronomers use to measure stellar distances, called parallax, works by watching how nearby stars appear to shift position as Earth orbits the Sun. It's remarkably effective for close stars, but as distances increase, these shifts become so tiny they're nearly impossible to detect. The galaxy seemed to be playing an elaborate game of hide and seek, with the scientists trying to map its true dimensions. For most of human history, nobody had ever seen a complete picture of our galaxy from the outside. Every image of the Milky Way as a whole spiral structure is actually an artist's interpretation, a careful reconstruction based on decades of measurements and observations. We're essentially trying to map a forest while standing in the middle of it, surrounded by trees and shadows that block our view of the bigger picture. Early models described our galaxy as a spiral structure about 100,000 light-years across, with several major arms curving outward from a bright central bulge. A vast halo of faint stars surrounds this disk like an invisible ocean, extending far beyond what we can easily observe. This model explained the movement of stars and gas clouds reasonably well, fitting most of the data astronomers had collected through radio waves and visible light observations. The scale of these measurements challenges our everyday understanding of distance and time. When we consider that light from some stars in our galaxy has been traveling toward us since before human civilization began, we start to grasp just how ancient and vast this cosmic neighborhood really is. Each point of light in the night sky represents a sun that might have planets, weather systems, and chemical processes we can barely imagine. Recent observations have begun to suggest that our galaxy might be larger and more complex than previous estimates indicated. The James Webb Telescope's infrared vision reveals structures that were invisible to earlier instruments, including star-forming regions and distant stellar populations that extend far beyond the traditional boundaries we've drawn on our galactic maps. There's something philosophically intriguing about the fact that we live inside the very thing we're trying to understand. Every measurement we make, every observation we record, comes from our position as inhabitants, rather than external observers. We're like researchers trying to describe the architecture of a building while being permanently confined to one of its rooms. The process of mapping our galaxy has been incremental and patient, built from tracking stellar movements, measuring gas cloud emissions, and watching how star clusters form and drift over time. Each small discovery adds another piece to a puzzle that spans hundreds of thousands of light years and billions of years of cosmic history. What emerges from this ongoing research is not just a map of stars and dust, but a deeper appreciation for the complexity and beauty of the cosmic structure we call home. Our galaxy continues to surprise us, revealing new layers of detail and unexpected features that remind us how much we still have to learn about our place in the universe. When astronomers look deeper into space, sometimes they find things that make them pause and reconsider what they thought they knew. Data has been building up, slowly but steadily, and it's painting a picture that doesn't quite match the tidy galaxy maps we've grown used to seeing. Out there, in directions where we expected emptiness, or at least much less activity, telescopes have been picking up faint signals from stars that are much, much farther away than anyone predicted. These aren't just a handful of lost stars that somehow wandered off, either. We're talking about entire populations of distant dim stars that seem to suggest our galaxy, the Milky Way, actually stretches way farther into the void than we ever imagined. The thing about these distant stars is that they're incredibly subtle. They don't announce themselves with bright, flashy light shows. Instead, they're quiet, patient points of light that only reveal themselves when you know exactly how to look, and when you're willing to wait for the right kind of evidence to accumulate. Now here's one of the trickier out how big a galaxy actually is. There's no clear finish line, no cosmic fence post that marks where the Milky Way ends and where everything else begins. It's not like looking at an island from an airplane, where you can clearly see the shoreline. Instead, what happens is that the density of stars just gradually gets thinner and thinner as you move outward. Those bright spiral arms that we see in all the textbook pictures, they eventually fade into scattered clusters. The main disk of the galaxy, where most of the action happens, slowly blends into something called a halo. This halo is filled with old, dim stars that orbit way out there, far from the galactic center. And beyond even that, you reach into galactic space, where the distances between individual stars become so enormous that the whole concept of calling it a galaxy starts to feel more like a gentle suggestion than a hard scientific fact. What's really changed the game is our ability to detect extremely faint infrared signals. This technology has made it possible to see parts of the galactic halo in much greater detail than ever before. And what's being revealed is that the Milky Way's influence, its gravitational reach, and its scattered population of ancient stars all extend much farther into space than previous measurements suggested. To really understand why this matters, it helps to think of the galaxy not as a flat picture in a textbook, but as a genuine three-dimensional structure floating in space. There's the thin disk, where most of the stars, gas and dust live their lives. That's where you find the spiral arms, where new stars are constantly being born, and where our own solar system happens to call home. Then there's what astronomers call the thick disk, which is kind of like a puffier, older layer of stars that sits both above and below that thin disk. And surrounding all of that is the halo, this vast, roughly spherical region that's filled with ancient stars and something much more mysterious. That mysterious something is dark matter, and it plays a quiet but absolutely crucial role in this whole story. Dark matter doesn't give off light, doesn't absorb light, and we can't see it directly through any telescope or instrument we've ever built. But we can definitely see its effects. And those effects are pretty dramatic. Stars in the outer parts of galaxies move faster than they should if only the visible matter, the stuff we can actually see, were providing the gravity to hold everything together. There's something else out there, something invisible, adding extra gravitational pull and keeping the galaxy from flying apart. That something is dark matter, and it likely makes up the vast majority of the galaxy's total mass. When modern telescopes observe the outer regions of the Milky Way, they're not just cataloguing stars, they're helping astronomers trace the shape and extent of this hidden structure. The farther out that stars are found orbiting in stable, predictable patterns, the more we learn about how far the galaxy's gravitational influence actually reaches. Recent studies, using data from multiple observatories, have suggested that the Milky Way's stellar halo could stretch hundreds of thousands of light years from the center. Now, that doesn't mean the space out there is packed with stars the way the inner galaxy is. What it means is that the galaxy's presence, its faint, quiet population of ancient stars, and its dark matter envelope reaches much, much farther into space than those bright, familiar spiral arms would suggest. It's a bit like suddenly realizing that the cozy, well-lit rooms of your house are surrounded by a sprawling, dimly lit yard that extends much farther than you ever noticed before. The house is still where most of the daily activity happens, but the actual property line is way, way out there, beyond what you can easily see from your kitchen window. There's another fascinating layer to this story, and it comes from looking not just at where stars are located, but at how they're moving through space. The Milky Way isn't floating alone in some empty cosmic void. It's surrounded by dozens of smaller satellite galaxies, like the Large and Small Magellanic Clouds, along with many faint dwarf galaxies that are so dim they're incredibly difficult to detect. These smaller systems orbit the Milky Way, drawn in by its massive gravitational pull. Sometimes they get stretched and torn apart in the process, like taffy being slowly pulled in different directions. Observations of stars in the far outskirts of our galaxy have helped astronomers identify streams of stars that don't quite fit the main rotational pattern of the Milky Way. These streams are actually the remains of smaller galaxies that wandered too close to our galaxy and were gradually pulled apart by tidal forces. Their stars now form long, faint trails that wrap around our galaxy like cosmic ribbons, telling the story of ancient gravitational encounters that played out over millions and millions of years. The presence of these stellar streams tells us something profound about the Milky Way. It hasn't always been the size it is today. It's not a static, unchanging object that's been sitting in space looking the same for billions of years. Instead, it's a structure that has grown over time by absorbing other galaxies, by slowly cannibalizing smaller neighbors that came too close. This is an ongoing process, a series of countless slow encounters, mergers, and gravitational dances that have been playing out for most of the universe's history. And this growth process directly contributes to the galaxy's true scale. The more material it absorbs, the farther its halo extends, the more dark matter it gathers, and the larger its overall gravitational footprint becomes. The ability to see these faint, distant stars makes these ancient interactions much easier to trace. It's like being able to read a history that's written not in words or documents, but in motion and light, in the paths that stars take as they orbit through the darkness. Now, it's worth taking a moment to think about where we fit into all of this cosmic architecture. Our solar system sits roughly 26,000 light-years from the center of the galaxy. That puts us far enough out that we're not in the crowded, energetic galactic core, where things can get pretty chaotic, but we're still well within the bright active disk, where star formation is happening and where most of the galaxy's visible activity takes place. We orbit the galactic center once every 230 million years or so. That's such a long time that since the first dinosaurs appeared on Earth, our sun has completed just one trip around the galaxy. Just one. From our particular position in this vast structure, we look out through layers and layers of stars, gas and dust. In almost every direction we point our telescopes. The night sky we see from Earth is directly shaped by this placement within the galactic disk. We see the Milky Way as that familiar bright band stretching across the sky because we're looking along the plane of the disk, where stars are most densely packed together. When we look up or down, away from that plane, the sky becomes noticeably darker and emptier. Because we're looking out of the disk and into the much more sparsely populated halo. These new discoveries gently remind us that even in those darker directions, where the sky seems mostly empty, the galaxy doesn't simply stop existing. It fades, certainly. It stretches out into something much more subtle. It becomes quieter and more sparse, but it continues, reaching much farther into the apparent emptiness than we ever realized. This idea of a galaxy without sharp, well-defined edges can feel a little unsettling, actually. We humans tend to like boundaries. We like knowing where things begin and where they end. We like clean categories and clear definitions, but the universe doesn't always cooperate with that very understandable preference. Structures in space often blur into one another in ways that can seem almost organic. Galaxies interact with their neighbors. Halos overlap and interpenetrate. Gravity weaves everything together into a kind of slow, continuous network of influence and interaction that operates on timescales we can barely imagine. In a strange way, learning that the Milky Way is much larger than we thought doesn't make it feel more distant or foreign. If anything, it makes it feel more present, more immediate. It means that the space around us, the cosmic environment we're moving through every single second as Earth spins on its axis and orbits the Sun, is part of a much bigger, much more extended system than those neat, tidy diagrams ever suggested. We're not just floating inside a disk of stars, like passengers on some cosmic ferry. We're embedded within a vast layered structure that reaches far out into the dark spaces between galaxies, connecting us to regions of space that seemed impossibly remote just a few years ago. And this is really only the beginning of what these new observations are starting to reveal. Data is still accumulating, flowing in from multiple telescopes and instruments. New datasets are being analyzed by teams of astronomers around the world. Patterns are being checked and double-checked and compared against theoretical models. Science moves slowly in areas like this, not because scientists are uncertain or confused, but because they're being extremely careful. Each new claim about the galaxy's size and structure has to be supported by multiple lines of evidence, from different instruments and different observational methods. Everything has to fit together into a coherent picture before anyone gets too excited about announcing major discoveries. As that careful work continues over the coming years, our picture of the Milky Way will keep shifting and evolving. Not in sudden, dramatic leaps that overturn everything we thought we knew, but in small, steady adjustments that gradually refine our understanding. A little farther in this direction, a little more mass calculated for that region, a newly discovered faint stream of stars added to the growing map, a previously unknown section of the halo traced in greater detail. If you let that idea settle for a moment, it has a surprisingly gentle, almost comforting effect. The galaxy isn't some fixed backdrop, like a painted stage set that never changes. It's a living, evolving environment, something we're moving through, something that's constantly changing around us on timescales far longer than a human lifetime, but not so long that they become completely meaningless. And as we follow this trail of thought, it naturally leads to other questions that don't demand immediate answers but instead invite us to wonder. If the Milky Way is significantly larger than we believed, if its structure is more layered and more extended and more complex than our models suggested, then what might that mean for how we understand our place within it and how we compare our home galaxy to all the others scattered throughout the observable universe? Our galaxy once seemed like a comfortable neighborhood, where astronomers knew the main streets and landmarks. For most of the last century, scientists carried a shared mental map of the Milky Way in their minds, confident that while small details might change, the big picture was settled. Open any textbook from 20 years ago, and you'll find that familiar diagram, clean and tidy, fitting perfectly on a single page. The roots of our galactic understanding stretch back to when people still wondered if the Milky Way was the entire universe. In the early 1900s, those faint, fuzzy spirals visible through telescopes sparked heated debates. Some astronomers thought they were just gas clouds floating within our own galaxy. Others suspected something far more profound, that these spirals were separate, island universes, scattered across an almost unimaginable vastness. Edwin Hubble settled this cosmic argument in 1924. He measured the distance to what we now call the Andromeda Galaxy, proving it lay far beyond our own stellar neighborhood. In that single moment, our galaxy transformed from being everything that existed to being just one among billions. It's hard to imagine how humbling that realization must have been, like discovering your entire world is actually just one house on an endless street. But understanding our own galaxy remained incredibly challenging because we're trapped inside it, like trying to map a forest while standing among the trees. The breakthrough came from studying globular clusters, those dense, spherical collections of ancient stars that orbit our galaxy's center. These stellar cities became cosmic lighthouses, helping astronomers navigate the darkness. When scientists plotted the positions of these clusters, they noticed something unexpected. The clusters weren't scattered evenly around our sun. Instead, they seemed to gather around a distant point in the constellation Sagittarius. That point marked the true heart of our galaxy, and suddenly, everything shifted. We weren't living near the galactic center as once believed. We were actually inhabitants of the cosmic suburbs, orbiting a distant, crowded downtown we could barely see. Harlow Shapley made this discovery in the 1910s, fundamentally changing our sense of place in the universe. The Milky Way became larger, more structured, and decidedly less centered on us than anyone had imagined. It's fascinating how each new discovery seems to nudge humanity further from any special cosmic position, as if the universe itself resists our desire to feel central to its story. As telescopes improved, astronomers began tracing the spiral arms of our galaxy by following the bright signposts of star formation. Young, massive stars burn hot and fast, like cosmic fireworks that illuminate the gas clouds where they're born. By mapping these stellar beacons and the glowing hydrogen surrounding them, scientists could sketch the rough outline of our galaxy's graceful arms. Over decades, a consensus emerged about our galactic home. 4 major spiral arms seemed to wind outward from the center, along with several smaller offshoots. The entire disk stretched about 100,000 light-years across, with a thick central bulge packed with stars and a long stellar bar stretching across the core, funneling gas inward to feed new generations of stars. This picture gained support from observations across the electromagnetic spectrum. Radio telescopes mapped invisible clouds of hydrogen gas. Infrared instruments peered through cosmic dust to reveal stars hidden near the galactic center. Optical telescopes catalogued nearby regions in exquisite detail. Each wavelength of light added another transparent layer to our growing map, like stacking see-through sheets to build a 3-dimensional understanding. Yet even as this image crystallized in textbooks and scientific papers, astronomers remained acutely aware of its limitations. Distance measurement in space is surprisingly tricky, almost like trying to judge how far away mountains are on a foggy day. For nearby stars, scientists use parallax, watching how stars appear to shift position as Earth orbits the Sun. This method works beautifully, but only out to a few thousand light-years. Beyond that, the shifts become too tiny for traditional instruments to detect. For more distant stars, astronomers rely on standard candles, cosmic objects whose true brightness is known. By comparing how bright these objects appear against how bright they should be, you can calculate their distance. Certain variable stars, like Cepheid variables, pulse in brightness according to predictable patterns, directly related to their luminosity, making them excellent cosmic measuring sticks. But every measurement carries uncertainty, like trying to measure a room with a slightly bent ruler. Dust dims starlight in unpredictable ways. Crowded stellar regions blur together. Different types of stars can masquerade as each other. Small errors in individual measurements can accumulate into larger uncertainties when you're dealing with millions of data points. So our map of the Milky Way was always somewhat fuzzy around the edges, painted in broad brushstrokes rather than fine detail. The challenge deepens when you realize our galaxy isn't frozen in place like a museum display. Stars drift along their orbits, gas flows between regions. Spiral arms shift, and evolve over cosmic time. The Milky Way resembles a vast slow-motion dance where everything moves and changes on timescales that dwarf human experience. Any map we create captures just one moment in this eternal choreography. This dynamic nature means our galactic portrait is always a temporary approximation, showing where things are now, not where they were millions of years ago, or where they'll be in the distant future. And because light takes time to travel across space, even now becomes a relative concept. When we observe a star 10,000 light-years away, we're seeing it as it existed 10,000 years in the past, like looking at an old photograph while the subject continues aging in real time. Our galaxy has always been like an ancient tapestry, woven from threads of different ages, all somehow coming together into one magnificent picture. For generations, astronomers felt they understood the basic blueprint, the spinning disk where we live, those graceful spiral arms, the central bulge packed with older stars, and the vast spherical halo surrounding it. All. There was something deeply reassuring about this consistency. Computer simulations could recreate how such a galaxy might grow and change over billions of years, and the results looked remarkably similar to what telescopes showed us. It felt like humanity had finally grasped the big picture of our cosmic home, even if countless small details remained mysterious. One of the most elegant ways scientists explored this structure was by watching how stars move through space. Every star in our galaxy follows its own orbital path, pulled and pushed by gravitational forces from all the mass around it. By carefully measuring these stellar motions, astronomers could work backwards to figure out where all that mass must be hiding. The results were absolutely startling. Stars living in the outer neighborhoods of the Milky Way were racing around much faster than they should have been. According to Newton's laws, if most of our galaxy's mass came from the stars and gas we could actually see, then those distant stars should crawl along much more slowly in their orbits. But they didn't crawl at all. They moved with surprising speed, as if some invisible hand was pulling them along. The only explanation that made sense required assuming enormous amounts of unseen mass, stretching far beyond the visible edges of our galactic disk. This became one of the strongest pieces of evidence for something called dark matter, a mysterious substance that apparently fills a massive, invisible cocoon around our entire galaxy. This discovery forced astronomers to completely reimagine what the Milky Way actually is. The true galaxy, it turned out, extends far beyond anything our eyes or cameras can detect. We can only sense its presence through the gravitational tugs and pulls it exerts on the stars we can see. In a very real sense, we live inside something much larger and stranger than we had ever imagined. As technology improved and surveys became more thorough, another surprise emerged from the darkness. Tiny dwarf galaxies began appearing in our cosmic neighborhood, most of them so faint they had remained hidden for decades. Some contained just a few thousand stars, barely qualifying as galaxies at all. Others revealed themselves only through subtle patterns in how nearby stars were moving, their gravity creating ripples that sharp-eyed astronomers could detect. Each newly discovered satellite galaxy added another piece to an increasingly complex puzzle. These small companions weren't just pretty decorations scattered around the Milky Way. They were witnesses to our galaxy's violent and hungry past. Over billions of years, our galaxy has grown by consuming smaller neighbors, pulling them apart with tidal forces and scattering their stars into long, graceful streams that now arch through the halo, like cosmic contrails. By carefully mapping these stellar streams, scientists could reconstruct ancient galactic encounters, figuring out when and where our galaxy had devoured its smaller companions. The Milky Way began to look less like a solitary island floating in space, and more like an active collector, shaped by countless slow-motion gravitational accidents. Despite all these discoveries, certain basic facts about our galaxy seemed well established. The visible disk appeared to stretch about 100,000 light-years from edge to edge. The dark matter halo extended perhaps twice that distance. The total mass came out to roughly 1 trillion times the mass of our Sun, with most of that mass locked up in the mysterious dark matter component. These numbers appeared everywhere, in research papers, textbooks, planetarium shows. They became part of astronomy's shared vocabulary, the standard answer to anyone curious about the scale of our galactic home. But science, by its very nature, builds knowledge that's always provisional, always ready to change when new evidence demands it. The biggest uncertainties lurked in the galaxy's outer reaches, particularly in that vast faint halo region. The stars out there are ancient and dim, spread incredibly thin across enormous volumes of space. Detecting them requires extremely sensitive instruments and painstaking analysis to separate genuine halo stars from distant background galaxies that might masquerade as local objects. For practical reasons, most surveys focused on the brighter, denser parts of our galaxy first. The disk and inner halo were relatively easy to map in detail. The far halo remained largely unexplored territory, a frontier where data points were scarce and scientific interpretations remained tentative at best. This created an interesting philosophical problem. Where exactly does the Milky Way end and empty intergalactic space begin? For a long time, astronomers defined those boundaries based largely on where their observations simply ran out of steam, not necessarily where the galaxy itself truly faded into the cosmic background. It was a boundary of convenience, rather than cosmic reality. Our perspective as residents of the galactic disk also creates unique challenges. When we look along the plane of the Milky Way, we see it edge on, like trying to understand a dinner plate by staring at it from the side. Only when we look up or down from the disk can we get face-on views, and even then, only of small patches. Getting a truly global sense of our galaxy's shape and size is remarkably difficult from our embedded viewpoint. Astronomers have developed ingenious methods to compensate for this limitation, using star counts, motion measurements, and sophisticated computer models of galactic structure. But every method relies on certain assumptions, and those assumptions can subtly influence the final results in ways that aren't always obvious. Consider the challenge of estimating how many stars actually live in the Milky Way. Scientists have to take careful measurements of the regions they can observe clearly, then extrapolate those findings to the vast regions they can't see well. If the actual density of stars in the far halo turns out higher or lower than expected, the total count changes dramatically. Similar uncertainties affect mass estimates based on measuring how fast stars and gas move at large distances from the galactic center. These limitations didn't mean the traditional model was wrong, exactly. It represented the best possible guess based on incomplete information, which is often how science works. Another approach involved comparing our galaxy to similar spiral galaxies elsewhere in the universe. Astronomers could observe these distant cousins face-on, measuring their properties and using them as reference points for understanding the Milky Way. If those external galaxies showed certain characteristics, it seemed reasonable to assume our galaxy might be similar. This comparative method helped fill important gaps in our knowledge, but it also introduced new assumptions. Our galaxy might be fairly typical among spiral galaxies, or it might be somewhat unusual in ways we haven't recognized yet. Without being able to step outside and look back at the Milky Way from a distance, it's surprisingly hard to be certain. Eventually, more advanced surveys began chipping away at these long-standing uncertainties. Space missions started measuring the precise positions and motions of over 1 billion individual stars, creating incredibly detailed three-dimensional maps of our galactic neighborhood. This revealed streams, clusters, and subtle structures that had never been detected before. These new observations showed that the Milky Way's disk isn't perfectly flat and smooth, as once imagined. Instead, it's warped and rippled, like a vinyl record that's been left too long in summer heat. The data revealed that our galaxy has experienced recent close encounters with satellite galaxies, leaving behind waves of motion that are still propagating through the stellar population, like ripples on a cosmic pond. These discoveries added remarkable texture and complexity to our understanding. The Milky Way was no longer just a neat, orderly spiral galaxy. It emerged as something more dynamic and messy, a system constantly being shaped by ongoing gravitational relationships with its smaller neighbors. And yet, fundamental questions about scale remained tantalizingly open. How far out do those faint halo stars really extend? How large is the dark matter envelope that surrounds everything? At what point does our galaxy's gravitational influence truly give way to the broader cosmic web that connects all galaxies across the universe? For decades, astronomers pieced together our galaxy's portrait using whatever clues they could find. They watched tiny satellite galaxies dancing around the Milky Way, measuring their orbits to guess at the invisible mass pulling them along. These cosmic waltzes revealed something massive lurking in the darkness, a halo of matter we couldn't see directly. Deep sky surveys searched for the faintest stars hiding in the galaxy's outer regions. But these surveys were like looking through keyholes, covering only tiny patches of the vast celestial dome above us. From these fragments, a picture slowly emerged of our galaxy as a bright disk wrapped in a fuzzy, sphere-like envelope, extending maybe 200,000 or 300,000 light-years from the center. The story gets more complex when you consider our cosmic neighbors. The Milky Way doesn't exist in isolation, floating alone in empty space. Andromeda, our nearest large galactic neighbor, sits relatively close by in astronomical terms. These two massive structures create overlapping gravitational fields, like ripples from stones thrown in a pond that eventually meet and interfere with each other. Andromeda is actually drifting toward us on a collision course that will play out over billions of years. This future merger hints at something profound about galactic boundaries. Where exactly does one galaxy end and another begin? The edges aren't sharp lines drawn in space, but gradual transitions where one gravitational influence gives way to another. When most people talked about the Milky Way's size, they usually meant the bright, star-filled disk we can photograph and map with relative ease. The dark matter halo remained an abstract concept, acknowledged by scientists but rarely visualized in detail. It lived in the background of discussions, mentioned briefly before conversations moved on to more tangible topics. This understanding formed the foundation that astronomers built upon as new tools became available. The expectation was reasonable refinement, sharper images revealing familiar structures in greater detail. Better instruments typically confirm what we already know while adding layers of precision and clarity. Instead, observations from advanced telescopes began revealing something more surprising. The faint, distant regions that previous instruments couldn't quite reach started coming into focus. These weren't completely unknown territories, but rather the shadowy borderlands where our earlier maps grew uncertain and speculative. What emerged challenged the simple picture of a galaxy fading gently into darkness. The outer regions showed complex structures with their own patterns and histories. The halo appeared richer than expected, populated with more material arranged in ways that suggested dynamic processes at work over cosmic timescales. The gravitational reach of our galaxy extends much farther than the visible stars might suggest. This invisible architecture shapes the motion of everything within its influence, creating a web of forces that extends deep into what we might casually think of as empty space. None of this means the Milky Way suddenly changed overnight. Galaxies don't grow or shrink on human timescales. What expanded was our awareness, our ability to see and measure structures that were always there but remained hidden from our earlier instruments. Scientific understanding often progresses this way, through models that capture part of the truth before giving way to more complete pictures. Each generation of tools reveals new details that force us to revise our cosmic perspective. The galaxy we thought we knew wasn't wrong, exactly, but it was incomplete. These discoveries remind us that even the most familiar objects in our cosmic neighborhood can still hold surprises. The universe has a way of exceeding our expectations, revealing complexity in places where we assume simplicity. Our home galaxy, the one structure we might expect to understand completely, continues to teach us about the nature of cosmic architecture. Perhaps there's something humbling in this, the realization that our own galactic home still keeps secrets from us. We live embedded within this vast structure, yet our perspective from inside makes certain truths difficult to grasp. Like trying to map a forest while standing among the trees, understanding the Milky Way requires patience and increasingly sophisticated tools to see beyond our immediate surroundings. The notion of measuring something from the inside creates one of astronomy's most perplexing puzzles. We exist as inhabitants of the very structure we're attempting to understand. It's comparable to wandering through fog-covered city streets, hearing distant sounds, catching brief glimpses of faraway buildings, but never being able to step back and see the complete picture spread before us. Distance becomes our first stumbling block. In daily life, we walk from here to there, we drive across familiar neighborhoods, we consult maps, and develop an intuitive sense of how far things are. Space obliterates this intuition completely. The nearest star beyond our sun sits more than 4 light-years away, roughly 40 trillion kilometers. These numbers stop functioning as measurements and become abstract mathematical concepts that our minds struggle to grasp. Parallax offers the most direct approach astronomers have developed. You've experienced this effect yourself. Holding your thumb at arm's length, closing one eye, then the other, watching your thumb appear to jump against the background. The closer your thumb, the bigger the jump. Earth's journey around the sun creates a similar effect with nearby stars, which seem to shift slightly against more distant, stellar backgrounds. Simple geometry can then calculate distances, but this shift becomes incredibly tiny, very quickly. Even relatively close stars produce shifts narrower than a human hair viewed from several kilometers away. Extremely precise instruments are required, and even then, parallax only works reliably within a few thousand light-years. This covers our local stellar neighborhood, while the galaxy stretches tens of thousands of light-years across. Beyond parallax's reach, astronomers turn to indirect methods. Standard candles become crucial tools, objects whose true brightness we know. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance. Light spreads out as it travels, making distant objects look dimmer. Certain star types prove especially useful. Cepheid variable stars pulse in brightness, following regular patterns. Their pulsation period directly relates to their true luminosity. Measure how fast they brighten and dim, and you determine their actual light output. Type 1 supernovas provide another standard candle. Stellar explosions that reach consistent peak brightness. These shine so brilliantly they can be seen in other galaxies, making them valuable for measuring much larger distances. Even standard candles face limitations inside our galaxy. Cosmic dust interferes, absorbing and scattering light, making stars appear dimmer and sometimes redder than they truly are. If you don't account for this correctly, you underestimate stellar brightness and overestimate distance. Dust distributes unevenly, clumping into clouds, filaments, and thick bands, especially along the galactic plane. Some sightlines remain relatively clear, while others are heavily obscured. Two stars at identical distances can look completely different depending on how much dust lies between them and us. Every distance measurement becomes a small puzzle. How much dimness comes from distance? How much from dust? Astronomers build dust distribution models to correct for this, but those models rely on observations that are themselves affected by dust. It resembles trying to map fog density while standing inside the fog. Crowding creates additional problems. The galaxy grows dense, especially toward the center. Some regions pack so many stars into small sky areas that they blur together. A telescope might see what appears to be a single, bright spot, but that light could actually come from dozens or hundreds of overlapping stars. Separating these stars requires high resolution and careful data processing. Even with modern instruments, it's not always possible to disentangle every individual source, particularly in the most crowded galactic core regions. This makes creating clean three-dimensional maps difficult. Instead of crisp, clear pictures, astronomers often work with probability layers. This star likely sits at this distance within a certain error margin. That cluster probably lies in this spiral arm region, but could be closer or farther than we think. When you scale this up to millions or billions of stars, uncertainties begin shaping the overall model of galactic size and structure. Motion adds another complexity layer. Nothing in our galaxy stands still. Stars orbit the galactic center. Gas clouds swirl and collapse. Satellite galaxies drift around us, sometimes passing close enough to disturb the disk. By measuring stellar motion, astronomers learn about galactic mass and shape through spectroscopy, splitting starlight into component colors. These color patterns reveal stellar velocity through the Doppler effect. Stars moving toward us show light shifted toward the blue spectrum end. Stars moving away show red shifted light. Measuring this shift calculates radial velocity, speed along our sight line, combined with position measurements and proper motion across the sky. This builds three-dimensional trajectory pictures through space. This technique proves incredibly powerful, but remains data-heavy and error-sensitive. Small velocity measurement mistakes can create big orbital differences over long timescales. When astronomers examine the galaxy's outer parts, they often rely on stellar and satellite galaxy motion to estimate interior mass. This resembles estimating Earth's mass by measuring lunar orbit. Faster orbital motion indicates more interior mass needed to maintain gravitational hold. If a dwarf galaxy zips around our galaxy at high speed, far from the center, this suggests lots of mass extending to that distance, even invisible mass. This method has been crucial for estimating our galaxy's dark matter halo size, but it depends on assumptions. You must assume the measured object maintains stable orbit and that you understand the acting forces. If a satellite galaxy is being torn apart or recently passed close to another massive object, its motion might not reflect the smooth underlying gravitational field. Even gravity, so reliable in everyday life, becomes a subtle and nuanced tool when dealing with structures spanning hundreds of thousands of light years. There's also the issue of defining what size actually means for a galaxy. When we say our galaxy measures a certain number of light years across, what exactly are we measuring? Are we talking about the bright stellar disk, the faint old star halo, the invisible dark matter envelope, or the region where galactic gravity dominates over neighbors? Each component has a different boundary, and none have sharp edges. The disk fades, gradually. The halo thins slowly. Dark matter extends far beyond the last visible star, blending into neighboring galactic dark matter halos. Our galaxy's gravitational influence overlaps with Andromeda and other nearby systems. Any number attached to galactic size becomes, to some extent, a choice. It reflects definition, rather than absolute physical boundary in space. This explains why different sources sometimes give slightly different figures for our galaxy size and mass. They may measure different components, or use different criteria for where the galaxy ends. Time itself complicates matters further. But time itself complicates matters further because light takes time to travel. We never see the galaxy as it exists right now. We see nearby stars as they were years ago. We see the galactic center as it was 26,000 years ago. We see distant halo stars as they were hundreds of thousands of years ago. For most practical purposes, this doesn't matter. Galaxies don't change dramatically on those timescales. But when building precise models, your map becomes always a collage of different past moments. It's like making a family portrait using photographs taken over several decades. The overall family shape is there, but details reflect different life stages, different expressions, different frozen moments in time. Background confusion presents another problem. Looking toward the galactic edge, you're not just seeing our galaxy, you're also seeing distant galaxies, far beyond it. Some faint points in deep surveys aren't galactic stars at all. They're entire galaxies millions or billions of light years away. Distinguishing between very distant galaxies and very faint nearby stars can be surprisingly difficult. Both can appear as small, dim light smudges. Astronomers use color, motion, and spectral signatures to tell them apart. But those methods require high-quality data and careful analysis. Misidentifying background galaxies as halo stars, or vice versa, can skew estimates of how many stars our galaxy has in outer regions, and therefore how far it extends. All this creates a situation where every measurement becomes part of a larger inference web, Astronomers don't measure one thing and declare galactic size. They combine data from multiple sources across different wavelengths, using various methods, then build models that best fit all that information. These models get tested, revised, and sometimes replaced as new data arrives. New instruments make tremendous difference here. A telescope seeing in new spectral parts, or with higher sensitivity, can break through old limitations. It can reduce uncertainties, reveal hidden structures, and challenge assumptions built into earlier models. Advanced space telescopes do exactly this by operating primarily in infrared wavelengths. Because infrared light passes through dust more easily than visible light, these instruments can see stars and structures previously obscured. They can peer into dense regions near the galactic center and into dusty disk and halo areas that older telescopes struggle to penetrate. They can also detect extremely faint sources, pushing the boundary of what counts as visible in our galaxy. This makes it possible to identify stars in the far halo reaches and study the distribution of faint, low-mass stars that comprise a large fraction of the galaxy's population. By combining this data with information from missions excelling at measuring positions and motions, astronomers create much more detailed three-dimensional maps. They can trace not just where stars are, but how they move and relate to overall galactic structure. This begins turning our galaxy from rough sketch into something closer to a living atlas, a dynamic model showing not just static features, but flows, streams, and subtle motion patterns. Still, even with these advances, the fundamental challenge remains. We are inside the system. We cannot step outside and take a single clean photograph. We must infer the whole from parts, and those parts are always filtered through distance, dust, motion, and time in ways that make the process profoundly human. It's not about finding a final perfect answer. It's about gradually refining, understanding, filling gaps, and remaining willing to adjust our picture as new information arrives. When you hear that our galaxy might be larger than previously thought, what that really means is that our methods have improved enough to reach a little farther into the darkness. We're seeing stars that were always there, but were previously hidden or too faint to detect. We're tracing gravitational influences that were always shaping the galaxy, but were hard to map with older tools. The galaxy hasn't changed. Our view of it has. If measuring our own galaxy proves this complex, this layered with uncertainty and interpretation, what does that reveal about how we understand our place within it, and how our own perspective shapes the cosmic picture we construct? Perhaps the most profound realization is that knowledge itself becomes a kind of exploration from within, always partial, always growing, always dependent on where we stand and how we choose to look. Since humans first glanced upward on clear nights, we've carried this quiet belief with us. What our eyes can capture, what our tools can eventually measure, that's what's really out there. The universe feels like something we can slowly wrap our minds around, piece by piece. But galaxies don't follow the rules of everyday size. The Milky Way isn't big like a skyscraper is big, or even like a continent is big. It exists in a category of largeness that has no place in normal life. Light years, hundreds of billions of stars, eons of time, these aren't things you can touch or walk around. They're concepts we handle through comparisons and careful mental gymnastics. Our brains evolved to keep us alive on a world that's 8,000 miles across. We're excellent at judging how far away that tree is, or whether something is moving in our peripheral vision. We're not built to naturally grasp something so vast it could swallow our entire solar system without noticing. When scientists talk about galactic scale, they're not just working with data and instruments. They're translating something fundamentally beyond human experience into something we can somehow understand. It's like trying to describe the ocean to someone who's never seen water. Most people picture our galaxy as a flat spiral, like a glowing pinwheel, suspended in darkness. That mental image works for basic understanding. It shows the arms, the center, the general shape. But it flattens something that actually has incredible depth and complexity. The Milky Way's disk isn't paper thin. It has layers, structure above and below, where most stars live. The halo wraps around everything in a faint, spherical embrace. Dark matter stretches even further out, invisibly shaping how everything moves. When we draw the galaxy on screens or pages, we squeeze all that richness into a symbol, and symbols, by their very nature, leave out most of what they represent. There's another layer of perspective that comes from where we sit. We're not floating outside, looking at the galaxy like a sculpture in a museum. We're embedded deep inside it, moving along our own particular path, peering out through layers of stars, gas, and cosmic dust. The Milky Way doesn't present itself to us as a neat object with clear edges. Instead, it shows up as a sky full of points of light, with the familiar glowing band stretched across the darkness. Everything we know about the galaxy's true shape has to be pieced together from this inside view. Imagine standing on one street corner in a massive city, trying to understand the entire urban landscape just by watching traffic and looking at nearby buildings. You might notice that cars flow in certain directions, that tall structures cluster in one area. Over time, you could build a mental map of where downtown might be, where the suburbs start, but there would always be neighborhoods you couldn't see directly, places you'd have to guess about. That's essentially our situation with the Milky Way. We watch how stars move, we measure light getting absorbed and scattered, we track gas clouds and smaller galaxies orbiting around us. From these clues, we build models of the whole structure, and like any model, it reflects not just the thing being studied, but also the limitations of whoever is doing the studying. Humans are remarkably good at thinking in relative terms. Big and small only make sense when we compare things. A house seems large next to a person, a mountain dwarfs a house, Earth dwarfs a mountain. But when you reach galactic scales, those familiar comparisons start breaking down completely. Earth sits about 8 light minutes from the Sun. The Sun is roughly 4 light years from its nearest stellar neighbor. The Milky Way stretches about 100,000 light years across its bright disk, much more when you include the halo. Each step up, that ladder isn't just an increase, it's a leap into an entirely different category of existence. Our intuition doesn't scale smoothly across these vast jumps. That's why descriptions of galaxies rely so heavily on analogies. If the solar system were the size of a coin, the Milky Way would span a continent. If the Sun were a grain of sand, the next star would be miles away. These comparisons help, but they also highlight just how removed the real numbers are from anything we can directly experience. Another limitation comes from time itself. We think in years, decades, maybe centuries, if we're considering history. The Milky Way has been around for billions of years. It was forming stars, absorbing smaller galaxies, reshaping itself long before Earth even existed. When we observe our galaxy, we're seeing it in just one particular moment of an incredibly long life. Even the light reaching our eyes carries messages from the past. That star you notice in the night sky, you're not seeing it as it is right now. You're seeing it as it was when its light began the journey to your eyes. For stars scattered across the galaxy, that light might have started its trip tens of thousands of years ago. The galactic center, 26,000 light-years away, appears to us as it was when early humans were first painting on cave walls. So the Milky Way, as we observe it, is really a patchwork of different moments in time, all layered together. Nearby stars show us the relatively recent past. Distant stars in the halo let us glimpse much further back. We never get to see the whole galaxy as it exists in a single unified moment. We're always looking through its history, piece by piece. Our attention shapes what we discover too. For decades, astronomers naturally focused on the brightest, most active parts of the galaxy. Star-forming regions, the dramatic center with its massive black hole, the main spiral arms. These areas are visually striking and scientifically rich. They tell us about stellar birth, black hole behavior, how gas flows through cosmic space. But while focusing on these cosmic fireworks, we naturally paid less attention to the quiet outskirts. The halo, with its sparse collection of ancient stars and faint streams of matter, didn't demand the same immediate attention. Studying it required deeper surveys, more sensitive equipment, and the willingness to spend time on regions that seemed relatively peaceful. This isn't a flaw in how we do science, it's just how exploration tends to work. We're drawn to where the action is, to the obvious drama, not the seemingly empty spaces around it. But as our tools become more sophisticated, like the James Webb Telescope, our attention can shift to these previously overlooked regions. When that happens, our picture of the galaxy starts changing, not because the Milky Way itself has transformed, but because we're finally noticing parts that were always there, waiting quietly in the background. Even the language we use carries hidden assumptions. We talk about the edge of the Milky Way as if galaxies were solid objects with clear boundaries. We describe galactic shape as if it were something you could pick up and rotate in your hands. In reality, a galaxy is more like a distribution of matter and energy. Its density varies gradually. Its influence fades rather than stopping abruptly. Its form depends entirely on which component you're examining. Stars have one distribution, gas another, dust yet another, and dark matter extends furthest of all. When we say the Milky Way has a certain size, we're usually talking about one particular component, typically the bright disk of stars. Other parts reach much further out. This layered, complex nature doesn't fit into simple descriptions. It requires more nuanced language, and nuance can be challenging to communicate. There's also a cultural dimension that colors our perspective. For most of human history, the Milky Way wasn't a scientific object at all. It was a feature of the night sky, woven into myths, stories, spiritual beliefs, a path for souls, a river of light, a bridge between worlds. When science began describing it as a galaxy, a gravitationally bound system of stars, that didn't erase those older meanings. It just added another layer to them. Even today, when we discuss our place in the galaxy, there's often a subtle emotional undertone. We are a tiny part of something incomprehensibly vast. We're not at the center of anything special. We're one star among hundreds of billions. This realization can feel humbling, comforting, or unsettling, depending on your perspective. Those feelings can quietly influence how we approach the science itself. There's a tendency to focus on the galaxy's central regions, where the supermassive black hole lives, where star formation runs intense, where everything feels dramatic and significant. The outskirts can seem like a quiet periphery, less interesting, less important, but from another angle, those distant regions are actually a record of galactic history. They preserve the remnants of ancient collisions and interactions. They harbor some of the oldest stars, relics from the Milky Way's early formation days. What appears peripheral from one viewpoint becomes central from another. This shifting sense of what matters reflects human perspective once again. We bring our own values, interests, narratives to how we study the universe. Even the technology we build embodies these choices. Telescopes get designed with specific goals, some optimized for visible light, others for radio waves, others for infrared. Each instrument opens a different window onto galactic structure. When a new window opens, like the one James Webb provides, it doesn't just add details to our existing picture. It can transform the entire image by revealing previously invisible features. That's why discovering the Milky Way might be larger than we thought isn't just a technical update, it's a genuine shift in perspective. It reminds us that our mental image of the galaxy gets shaped by what our tools allow us to detect. There's a parallel. In everyday life, a city feels completely different depending on how you explore it. Drive only on major highways, and you get one impression. Walk through neighborhoods, parks, and side streets, and you discover something entirely different. Neither view is wrong, they're just partial. Similarly, our view of the Milky Way has been shaped by the major highways of astronomical observation. The bright stars, active regions, easily detectable structures. As we begin wandering into fainter, quieter cosmic neighborhoods, our sense of the whole naturally changes. The Milky Way itself sits within even larger structures. The local group of galaxies, including Andromeda, Triangulum, and dozens of smaller systems. That group belongs to a vast filament of galaxies, which forms part of an enormous cosmic web stretching across the observable universe. So even as we struggle to fully comprehend our own galaxy's scale, that galaxy is just one node in a much grander pattern. This creates a kind of nested perspective, where every time you think you've grasped the edge of something, you discover it sits inside something even more immense. From Earth's surface, the sky feels infinite. From the solar system's perspective, Earth's orbit is a small loop around a single star. From the galaxy's viewpoint, the solar system becomes a tiny point among hundreds of billions. From the universe's scale, the Milky Way is one among trillions of galaxies. At each level, what felt enormous becomes small. This doesn't mean our original perspective was mistaken. It was just operating within certain limits. In science, recognizing those limits is part of the fundamental process. Every measurement, every model, every theory comes with boundaries where it works well, and beyond which it becomes less reliable. When astronomers revise their estimates of galactic size, they're not admitting mistakes. They're doing exactly what science is designed to do, adjusting models to better match evidence. There's something quietly reassuring about this process. It suggests our understanding isn't frozen in place. It can grow and evolve. That growth often begins at the edges, in places where our perspective has been weakest. The faint stars at galactic outskirts, the subtle motions of distant companion galaxies, the barely detectable glow of ancient stellar populations. These are the regions where our assumptions face their greatest challenges, precisely because they're the places we've seen least clearly. James Webb's contribution to this story isn't just that it sees farther, it sees differently. By working in infrared wavelengths, it sidesteps some of the barriers that have shaped earlier perspectives. It reduces dust interference, highlights cooler and fainter objects, brings previously hidden parts of the galaxy into view. As those hidden regions become visible, the balance of our cosmic picture shifts. The bright, familiar structures remain, but now they're set within a larger, more extended context. This feeds back into how we understand our own position. We're not just located in a spiral arm of some galaxy. We're part of a layered, evolving system with deep history and wide reach. We belong to a structure that extends far beyond what we can see with our eyes, or even with most of our instruments. This doesn't change the fact that your immediate surroundings remain exactly the same size they were before. Earth still turns, the night sky still looks familiar. But it adds a quiet, expanded background to those everyday experiences. When you look up at that band of light we call the Milky Way, you can think of it not just as a stripe across darkness, but as the dense middle section of a much larger, more subtle presence surrounding you on all sides. If our perspective has limits, that doesn't make it worthless. It makes it a starting point. Every new observation, every improved instrument, every refined model becomes a way of stepping slightly further from that starting point, gaining a somewhat wider view of where we actually are. The universe holds secrets behind veils of cosmic dust, secrets that have puzzled astronomers for generations. These thick curtains of interstellar material scatter and absorb the light we're most familiar with, creating dark patches across our view of space. It's a bit like trying to understand a vast city while looking through heavy fog. You can make out the brightest landmarks, but entire neighborhoods remain hidden. For decades, scientists knew exactly what they needed to pierce through this cosmic haze. They needed eyes that could see in wavelengths longer than visible light, eyes that could detect the infrared radiation that passes through dust like sunlight through a window. The concept seemed straightforward enough, but turning that idea into reality would demand years of engineering innovation and technological breakthroughs that pushed the boundaries of what seemed possible. Temperature becomes your enemy when you're hunting for infrared light. Everything warm glows in these wavelengths, including the telescope itself. Imagine trying to spot fireflies while holding a bright flashlight. That's essentially the challenge facing infrared astronomy. The solution requires cooling instruments down to temperatures so extreme they approach absolute zero, the theoretical point where all molecular motion stops. This cooling requirement shapes everything about how such an observatory must operate. Earth's vicinity, with its constant cycle of sunlight and shadow, creates temperature swings that would ruin sensitive infrared detection, so engineers had to think beyond Earth orbit entirely, sending their creation to a point in space nearly 1 million miles away, where the gravitational influences of Earth and Sun create a stable parking spot. At this distant location, a spacecraft can maintain a fixed orientation relative to both Earth and Sun, keeping a massive shield between its instruments and all sources of heat. This shield, roughly the size of a tennis court, consists of 5 separate layers, each designed to reflect and radiate away thermal energy. By the time any warmth reaches the telescope on the protected side, it has been reduced to almost nothing. The engineering challenges multiply when you consider the mirror needed to collect faint infrared signals. Larger mirrors gather more light, revealing fainter objects and finer details, but no launch vehicle could accommodate a single mirror of the required size. The solution involved creating a segmented mirror that folds up for launch, then unfolds and aligns itself in the vacuum of space. 18 hexagonal segments, each coated in gold for optimal infrared reflection, must work together as a single optical surface. The precision required defies everyday understanding, each segment positioned to within fractions of the width of human hair. Tiny motors called actuators continuously adjust these segments, maintaining perfect alignment despite the harsh environment of space. The deployment sequence represents one of the most complex mechanical operations ever attempted beyond Earth. Hundreds of individual steps must occur in perfect order, with no possibility of human intervention if something goes wrong. Motors that have never operated in vacuum must turn, cables must unreel smoothly, and hinges must move precisely, all while subjected to the temperature extremes of space. Gold plays a fascinating role in this cosmic engineering. This precious metal, valued by human civilizations for millennia, proves ideal for reflecting infrared radiation. Each mirror segment receives a coating of gold atoms just a few hundred nanometers thick, thinner than a soap bubble but crucial for the telescope's performance. It's remarkable how an element prized for jewelry and currency becomes essential for exploring the deepest mysteries of space. When infrared light finally reaches the telescope's instruments, it undergoes a transformation from cosmic radiation to digital data. Specialized detectors convert individual photons, particles of light that may have traveled for thousands of years, into electronic signals. These signals become numbers in computer files, which eventually become the images and graphs that reveal the universe's hidden structures. Different infrared wavelengths tell different stories about the cosmos. Just as visible light comes in various colors, infrared radiation spans a range of wavelengths, each carrying unique information. Some wavelengths reveal the temperature of distant objects, others show their chemical composition. By observing the same region at multiple infrared wavelengths, astronomers can separate different components and understand complex physical processes. Dust, the very obstacle that motivated infrared astronomy, becomes transparent at these longer wavelengths. Regions that appear as dark voids in visible light photographs suddenly reveal intricate structures when viewed in infrared. Networks of gas filaments, knots of forming stars, and cavities carved by stellar winds emerge from what once seemed like empty space. The collaboration between space-based observatories creates a kind of cosmic depth perception. While one mission measures precise positions and motions of stars, another reveals their temperatures, compositions, and evolutionary stages. This combination transforms flat star maps into 3 dynamic models of galactic structure. Faint stellar populations in the outer regions of our galaxy previously below detection limits become visible to sensitive infrared instruments. These ancient dim stars formed when the universe was younger, carrying information about cosmic history in their light. Finding and characterizing these distant stellar citizens helps astronomers understand how far our galaxy's influence extends into space. The synergy between different observational approaches reveals structures that no single technique could detect alone. Streams of stars, remnants of smaller galaxies torn apart by gravitational forces, become easier to trace when their faintest members can be reliably identified. Subtle patterns in stellar populations across vast distances offer clues about when and where different parts of our galaxy formed. Dark matter, that mysterious component that outweighs visible matter throughout the universe, leaves its signature in the motions of stars and satellite galaxies. By combining precise position measurements with detailed infrared observations, astronomers can better map where visible matter actually resides, leading to more accurate inferences about dark matter distribution. The process of turning observations into understanding involves layers of interpretation and analysis. Raw telescope data undergoes extensive processing before becoming the striking images that capture public attention. This doesn't diminish their scientific value. Rather, it reflects the sophisticated conversation between human ingenuity and cosmic phenomena. Scientific progress in astronomy often appears slow from the outside, with discoveries announced, revised, and debated over years or decades. But this careful, evidence-based approach ensures that our understanding builds on solid foundations rather than speculation. Each new observation adds another piece to an enormous cosmic puzzle. The same instruments designed to study the most distant galaxies in the universe also prove invaluable for exploring our own galactic neighborhood. In some ways, the Milky Way becomes a nearby laboratory where processes that shape all galaxies can be observed in unprecedented detail. This connection between local and cosmic phenomena exemplifies how astronomical research reveals universal principles. Photons, those fundamental packets of electromagnetic energy, serve as messengers carrying information across vast distances and time spans. Some of the infrared radiation collected by space telescopes began its journey when our galaxy was significantly younger, when the arrangement of stars and gas bore little resemblance to what we see today. The human perspective on these cosmic scales challenges our intuition in profound ways. We live our lives in terms of years and decades, yet study objects whose evolution spans millions or billions of years. We inhabit a planet just over 12,000 kilometers across, yet probe structures extending hundreds of thousands of light years through space. This vast difference in scales creates both intellectual excitement and philosophical wonder. How do we, as brief inhabitants of a small world, come to understand systems so enormous and long-lived? The answer lies partly in technology, but perhaps more importantly, in our capacity for abstract reasoning and mathematical analysis. The continuing operation of advanced space observatories promises to refine and expand our understanding of galactic structure and evolution. Future surveys will map stellar populations in greater detail, trace chemical gradients across vast distances, and reveal how our galaxy compares to similar systems throughout the universe. Each new dataset brings opportunities to test theoretical models against observational reality. Sometimes observations confirm predictions, validating our understanding of physical processes. Other times, unexpected results force scientists to reconsider fundamental assumptions about how galaxies form and evolve. The story of infrared astronomy reflects a broader theme in scientific exploration: the gradual expansion of human perception beyond its natural limits. We evolved to see a narrow slice of the electromagnetic spectrum, but through ingenuity and technology, we've learned to detect radiation across wavelengths, from radio waves to gamma rays. This expansion of observational capabilities invariably reveals phenomena that were completely unknown before. Dark matter itself remained hidden until astronomers developed techniques for measuring the motions of stars and galaxies with sufficient precision to detect gravitational influences from invisible mass. The question of our galaxy's size, seemingly straightforward, actually touches on deep issues about the nature of cosmic structures. Galaxies don't have sharp edges like planets or stars. Instead, they fade gradually into the sparse matter of intergalactic space. Defining where one ends and the other begins requires careful consideration of what we mean by membership in a galactic system. Different components of our galaxy extend to different distances from the galactic center. The thin disk of young stars and gas that contains our Sun extends perhaps 50,000 light-years outward. The thick disk of older stars reaches somewhat farther. The stellar halo, containing the galaxy's most ancient stars, may extend several times farther still. Beyond even the stellar halo lies the dark matter halo, invisible except for its gravitational effects on visible matter. This dark component likely extends far beyond any stars, creating a vast reservoir of mass that helps bind satellite galaxies to our own. The true extent of this dark matter distribution remains one of the major uncertainties in determining our galaxy's overall size. These different components formed at different times in cosmic history through different physical processes. The central bulge and inner halo contain stars that formed when the universe was relatively young, and gas could collapse rapidly under its own gravity. The disk formed later, as gas settled into a rotating plane and continued forming stars over billions of years. Understanding this formation history requires connecting observations of our galaxy today with theoretical models of how cosmic structures evolve over time. The faint stars in our galaxy's outer regions serve as fossil evidence of ancient events, their chemical compositions, and orbital patterns, preserving information about the conditions that existed when they formed. The interplay between observation and theory drives astronomical progress forward. Observations provide the raw material for understanding, but interpreting those observations requires theoretical frameworks that connect what we see to underlying physical processes. When observations and theory agree, confidence in our understanding grows. When they disagree, new discoveries often follow. Scattered throughout the void between the stars, countless tiny grains drift silently through space. These particles are smaller than specks of smoke, yet they hold tremendous power over how we see our galaxy. Each grain contains elements forged in the hearts of dying stars, carbon and silicon, traces of metals, fragments of ice. When massive stars explode or gentle giants shed their outer layers, they release these materials into the cosmic wind. What happens next shapes everything we know about the Milky Way. The dust doesn't just float harmlessly in space. It actively interferes with light traveling across vast distances. When starlight encounters these microscopic obstacles, something fascinating occurs. Blue light, with its shorter wavelengths, gets scattered and absorbed much more readily than red light. This means that distant stars appear redder and dimmer than they actually are, a phenomenon astronomers call interstellar reddening. Think about how this affects our understanding of the galaxy's true size. Entire regions become invisible in ordinary light, hidden behind curtains of cosmic dust. The central parts of the Milky Way, where stars crowd together in incredible density, remain largely mysterious to telescopes that see only visible light. It's as if we're trying to map a vast city while looking through layers of fog. For generations, astronomers knew something important lay behind these dark patches. They could see the bright regions clearly enough, but the shadowed areas held their secrets. The dust lanes that snake across photographs of our galaxy aren't empty spaces. They're actually some of the most active and interesting regions, packed with raw materials for future stars and planets. Infrared light changes everything. These longer wavelengths slip past the dust particles that block visible light, like small fish swimming through a net designed to catch larger ones. This property makes infrared astronomy incredibly valuable for exploring the hidden architecture of our galaxy. When the James Webb Telescope was conceived, this ability to see through dust was one of its most important design goals. Before Webb, infrared observations came in fragments, pieces of a puzzle that never quite fit together completely. Ground-based telescopes struggle with Earth's atmosphere, which absorbs much of the infrared radiation from space. Earlier space missions provided glimpses, but lacked the sensitivity and resolution needed to reveal fine details. Webb's enormous mirror and sophisticated instruments changed this equation dramatically. Star-forming regions showcase this difference most dramatically. In visible light, these areas often appear as dark, empty patches, like holes torn in the fabric of the starry sky. But these apparent voids teem with activity. Inside dense clouds of gas and dust, gravity slowly pulls material together, forming the seeds of new stars. As these stellar embryos grow, they remain completely hidden within thick cocoons of surrounding matter. Only much later, when a young star becomes hot enough to blow away or illuminate its dusty envelope, does it finally shine in visible light. Infrared observations can peer into these stellar nurseries much earlier, watching the birth process unfold in real time. We can trace the delicate filaments of material feeding growing stars, observe the cavities carved out by stellar winds, map the complex shapes of these cosmic wombs. This capability reveals something profound about how galaxies sustain themselves. The cycle of stellar birth and death operates continuously across the entire Milky Way, from the crowded center to the sparse outer edges. Gas and dust condense into stars. Stars live their lives and die, returning enriched material back to space, where the cycle begins anew. By seeing through the dust, we can study this fundamental process in regions that were previously inaccessible. The distribution of dust itself tells a story. It's not spread evenly throughout the galaxy, like a uniform haze. Instead, dust concentrates along the spiral arms, where gas densities are higher and star formation more active. This creates the dark lanes we see in edge-on views of other spiral galaxies, thin lines that trace the underlying structure of the spiral pattern. Because we live inside the Milky Way, we see these dust lanes from the side rather than from above. They appear as broad, irregular bands stretching across large portions of our sky. This uneven distribution creates a kind of cosmic selection bias. Regions lying behind thick dust clouds are underrepresented in visible light surveys, while areas with clearer sightlines appear overrepresented. Infrared observations help correct this bias. By comparing how the same region appears in visible and infrared light, astronomers can estimate how much dust lies along that particular line of sight. This allows them to adjust the apparent brightness of stars, getting closer to their true luminosity and distance. These corrections can make significant differences in star counts and distance estimates, which directly affects how far the galactic disk and halo appear to extend. The galactic center presents the most extreme example of dust obscuration. This region, packed with stars and dominated by a supermassive black hole, remains largely invisible in ordinary light. Thick clouds of dust block our view almost completely, leaving only scattered bright stars and glowing patches to hint at the incredible activity beyond. Infrared telescopes have gradually revealed this hidden landscape over the years, but Webb adds unprecedented clarity to the picture. Better observations of the galactic center matter for understanding the galaxy's overall scale. The center serves as a key anchor point for models of galactic structure. Its mass, motion, and stellar distribution help define the orbits of everything else in the galaxy. More accurate data about the center leads to better models of the disk and halo, ultimately improving estimates of how far the galaxy's influence extends. Dust also affects how we distinguish between nearby stars and distant galaxies. When looking toward the outer regions of the Milky Way, especially at high galactic latitudes, astronomers encounter faint sources that could be either dim halo stars or entire galaxies billions of light years away. In visible light, these objects often look remarkably similar, appearing as tiny, blurry points. Infrared observations help solve this puzzle. Distant galaxies have different infrared signatures than nearby stars. Their light has been stretched by the expansion of the universe, shifting it toward longer wavelengths. They may also show the combined glow of billions of stars mixed with warm dust from within the distant galaxy itself. By analyzing the infrared spectrum of a faint source, astronomers can determine whether they're looking at a halo star or a distant galaxy. This distinction reduces confusion and makes star counts in the outer regions more reliable. These star counts are crucial ingredients in determining how far the galaxy extends into space. Every misidentified object skews our understanding of where the Milky Way ends and intergalactic space begins. Another form of darkness that infrared observations address comes not from dust, but from temperature. Many objects in space are simply too cool to emit much visible light. Low-mass stars, brown dwarfs, and certain types of stellar remnants shine primarily in infrared wavelengths. These objects can be numerous, especially in older populations like the galactic halo. Because they're faint and cool, they're easily missed in optical surveys, yet they still contribute to the galaxy's mass and structure. By detecting these cooler objects, Webb helps reveal a population of stars that were always there but often overlooked. This matters when astronomers try to estimate the total number of stars in the Milky Way and the distribution of mass across the galaxy. If a significant fraction of stars are faint and cool, then visible light surveys alone will systematically underestimate their presence, especially in distant or obscured regions. The emptiness between stars presents another challenge for defining galactic boundaries. The Milky Way is not a solid mass of light, but mostly empty space. Even in the densest regions of the disk, stars are separated by several light-years on average. In the halo, those distances grow much larger. This sparseness makes the galaxy's outskirts difficult to define precisely. When stars become very sparse, it becomes increasingly hard to tell where the galaxy ends and intergalactic space begins. Infrared sensitivity helps by allowing detection of stars that are both faint and isolated. A single star in the far halo might emit so little light that it disappears into background noise in visible images. In the infrared, it can stand out just enough to be identified and studied. Each such detection extends the known reach of the galaxy by a small amount. Over many observations, these small extensions can add up to significant revisions of the galaxy's scale. It's like finding scattered outposts of a vast territory, each discovery pushing the boundaries a little further into the wilderness. Dust temperature provides another layer of information. Dust grains absorb energy from nearby stars and re-emit it in infrared wavelengths. By measuring this emission, astronomers can estimate the temperature and density of dust clouds throughout the galaxy. Webb's instruments can map these properties across different regions, revealing variations that hint at different environments and evolutionary histories. In the outer parts of the galaxy, where star formation is less active, dust tends to be cooler and more diffuse. Detecting this faint emission challenges even sensitive instruments, but it provides valuable information about how far the galaxy's interstellar medium extends. If dust and gas are found far from the bright disk, it suggests that the galaxy's material envelope reaches farther into space than previously thought. The interplay between dust and the invisible dark matter halo adds yet another dimension to these observations. While dust doesn't interact directly with dark matter, both are influenced by the galaxy's gravitational potential. The distribution of dust and gas can trace the underlying shape of the dark matter halo in subtle ways, particularly in how material flows and settles over cosmic time. By mapping dust and gas in the galaxy's outskirts, astronomers can test models of the halo's shape and extent. Webb's ability to detect faint dust emission and obscured stars provides new data for these tests, helping refine our understanding of the invisible scaffolding that holds the galaxy together. There's something almost philosophical about the idea that much of our galaxy's true nature has been hidden behind veils of dust, waiting for different kinds of light to reveal it. For millennia, humans looked up and saw a glowing river of stars across the night sky. That view was fundamentally shaped by dust, which both blocked and highlighted different parts of the galactic landscape. Now with infrared vision, we're beginning to see beyond that surface into deeper layers that were always present but out of reach. This doesn't replace the familiar view of the Milky Way, it enriches it. The visible galaxy remains real and meaningful, still the way our cosmic home presents itself to human eyes on clear nights. The infrared Milky Way reveals different aspects of the same magnificent structure. As astronomers combine Webb's observations with data from telescopes across the electromagnetic spectrum, they're building something like a multi-layered map of the galaxy. Each wavelength contributes its own information. Radio waves trace cold gas clouds. Infrared light reveals dust and cool stars. Visible light shows hot young stars and glowing nebulae. Ultraviolet light highlights the most energetic processes and massive stars. When these layers stack together, the Milky Way emerges not as a simple shape in space, but as a complex system of interacting components, each with its own distribution and scale. In this layered view, the idea of a single, simple boundary becomes increasingly difficult to maintain. The galaxy doesn't end abruptly at some cosmic fence post. It fades gradually through populations of older stars, through thin streams of material, through a dark matter halo extending far beyond anything that emits light. By seeing through dust and darkness, Webb illuminates parts of this gradual transition, making the boundary between galaxy and intergalactic space less sharp and more nuanced. This represents one of the subtle ways a telescope can change not just what we know, but how we think about what we know. Rather than seeking a single number to describe the Milky Way's size, astronomers increasingly discuss different scales for different components. The stellar disk has one extent, the stellar halo another, the gas halo reaches even further, and the dark matter halo extends furthest of all. Each component has its own structure, its own uncertainties, its own story to tell. Infrared observations feed into all these scales by revealing stars, dust, and gas in regions that were previously difficult to study. As this information accumulates, our picture of the Milky Way becomes less like a neat textbook diagram and more like a complex landscape with gradual transitions and overlapping territories. That landscape continues to be mapped with each new observation, each deep survey adding more points of light to our growing understanding of this cosmic archipelago we call home. In the quiet spaces between constellations, where the night sky appears almost empty to our eyes, there exists an entire hidden universe of stars. These regions look calm, unremarkable, even like the galaxy has simply taken a breath. For centuries, astronomers treated these areas as background scenery, places where nothing particularly interesting was happening. But this assumption, it turns out, was profoundly wrong. The James Webb Space Telescope has begun to reveal what was always there, waiting in the darkness. When you shift your perspective from visible light to infrared, these seemingly empty patches transform into rich, complex landscapes filled with stellar populations that have been invisible to us for generations. It's a humbling reminder that our perception of reality is often limited by the tools we use to observe it. Red dwarf stars make up the majority of our galaxy's stellar population, yet they remain largely invisible to traditional telescopes. These small, cool stars emit most of their light in wavelengths our eyes cannot detect. A red dwarf sitting in the outer regions of the Milky Way might be so faint in visible light that it barely registers above the noise in an image, but in infrared, it suddenly becomes visible. A real physical object with its own story to tell. When you multiply this by millions of stars, you begin to understand how dramatically we may have undercounted the galaxy's true population. It's like trying to take attendance in a dark room with only a small flashlight, missing most of the people standing quietly in the shadows. The implications of this go far beyond simple star counting. When astronomers estimate the size and structure of the Milky Way, they rely heavily on where they can detect stellar populations. Where stars appear plentiful, the galaxy seems dense and present. Where they become sparse, the galaxy appears to fade away. If significant numbers of stars have been too faint to detect with older methods, then we may have been drawing the edges of our galaxy much closer than they actually are. The Milky Way is not a single generation of stars, but rather a layered structure built over billions of years. Think of it like an ancient city, where different architectural periods are stacked on top of each other, each telling part of the story. Some stars are young, hot, and bright, shining with intense bluish light. Others are ancient, small, and cool, having formed when the galaxy was young and the universe itself was a very different place. These older stars often populate the halo and thick disk regions, areas that are more diffuse and less visually dramatic than the main spiral arms we're familiar with. Because they're cool and dim, they're much easier to detect in infrared than in visible light. When Webb observes what looks like a simple patch of sky, it often reveals multiple populations of stars at different distances, belonging to different chapters of the galaxy's long history. This depth changes everything about how we understand the Milky Way's shape. Instead of seeing our galaxy as a relatively simple disk with a thin halo around it, we're beginning to recognize it as a much more complex, extended system where different stellar populations overlap and interweave like threads in an intricate tapestry. Some of these hidden stars carry within them the signatures of cosmic violence and galactic cannibalism. In the outer regions of the Milky Way, Webb has helped identify stars that don't quite match the chemical composition of stars formed in the main disk. They have different ratios of elements, like iron, carbon, and what astronomers call alpha elements. These differences tell a story of formation in environments with very different histories of star birth and stellar death. These are the remnants of smaller galaxies that were absorbed by the Milky Way long ago. Their stars scattered into long, faint streams that now wrap around our galaxy's halo like ghostly ribbons. In visible light, these streams are incredibly difficult to trace, especially where they pass behind dust clouds or blend into crowded star fields. But infrared observations can help separate these ancient immigrants from the surrounding local population by highlighting subtle differences in brightness and color. By mapping these hidden structures, astronomers are essentially uncovering our galaxy's family tree, seeing not just what the Milky Way is today, but understanding how it became what it is through billions of years of cosmic evolution and occasional acts of galactic consumption. Then there are the stars hidden not by distance or age, but by the very process of their birth. Star formation is an inherently messy affair. When a region of gas begins to collapse under its own gravity, it pulls in enormous amounts of dust along with it. The result is a dense, opaque cloud that can block visible light almost completely, creating what appear to be dark voids in the night sky. But these aren't empty spaces at all. Inside these dusty cocoons, new stars are forming, growing, and heating up, their light trapped and absorbed by the surrounding material. To a visible light telescope, these regions look like holes in the universe. In infrared, they become incredibly rich, detailed landscapes filled with clusters of young stars at various stages of development. Some of these stellar nurseries are wrapped in thick envelopes of material, like cosmic babies still in the womb. Others are beginning to clear out their surroundings with powerful radiation and stellar winds, announcing their presence to the galaxy. These discoveries often occur in regions that astronomers have studied for decades, but the level of detail that emerges in infrared can be startling. A familiar nebula might suddenly reveal dozens or hundreds of faint protostars that were previously invisible. Motion provides another clue to hidden stellar populations. Some stars in the Milky Way move at speeds that set them apart from their surroundings, like travelers on a cosmic highway, moving against traffic. These could be stars that were flung out of dense clusters by gravitational interactions, or remnants of past galactic mergers still following distinct paths through space. Because these stars often pass through regions that are otherwise sparsely populated, they can be easy to miss. Their light may be faint, and their presence might not significantly change the overall brightness of a patch of sky. But by combining Webb's infrared sensitivity with precise motion data from other missions, astronomers can identify these stellar wanderers more reliably. These moving stars act like breadcrumbs in a cosmic fairy tale, tracing out the paths of past interactions and helping define the extent of our galaxy's gravitational reach. Each one tells part of the story of how the Milky Way has grown and evolved through encounters with other cosmic structures. Not all stars shine brightly forever, and the galaxy is filled with the remnants of stellar death. When stars like our Sun reach the end of their lives, they shed their outer layers in beautiful displays of cosmic artistry, leaving behind dense cores called white dwarfs. These objects start out small and hot, then gradually cool over billions of years, like cosmic embers. Older white dwarfs can be extremely faint, especially in visible light, but they continue to emit in infrared wavelengths. Detecting these stellar remnants helps astronomers estimate how many stars have lived and died in different parts of the galaxy over cosmic time. If large numbers of white dwarfs are found far from the bright disk, it suggests that star formation was once more widespread than it is today, or that stellar populations have been redistributed by mergers and gravitational interactions. Perhaps even more intriguing are the objects called brown dwarfs, sometimes known as failed stars. These cosmic might-have-beens formed like stars, but never became massive enough to ignite the sustained nuclear fusion that powers true stars. They glow faintly, primarily in infrared light, and can be incredibly difficult to detect even with sensitive instruments. Brown dwarfs are thought to be numerous throughout the galaxy, potentially making up a significant fraction of its total population, while contributing almost nothing to its visible light. They represent a kind of dark matter made of ordinary matter, objects that add mass and gravitational influence to galactic structure, while remaining largely invisible to our traditional ways of seeing. All of these discoveries contribute to a gradual but profound shift in how we think about even the most familiar regions of the night sky. A constellation that humans have recognized for thousands of years might look exactly the same to the naked eye, but in infrared, it becomes a layered scene with stars at multiple distances, embedded clusters, faint streams of ancient immigrants, and cool objects that add incredible depth and complexity to what seemed simple. This layered view affects everything about how we measure cosmic distances. If a region contains multiple overlapping populations of stars, some in our galaxy's disk, some in its halo, and some in the far background, it becomes challenging to assign any single distance to that patch of sky. Each population needs to be carefully separated and analyzed on its own terms. Webb's ability to detect faint stars and determine their properties helps make this separation more accurate, allowing astronomers to build increasingly precise three-dimensional maps of our galaxy. These maps, in turn, directly affect estimates of the Milky Way's true size. If stars belonging to our galaxy are found at greater distances than previously thought, the boundary of the galaxy moves outward in that direction. This doesn't necessarily mean the galaxy is perfectly round or symmetrical. Different regions may extend farther or fall off more quickly, depending on how stars, gas, and dark matter are distributed. But each new detection of a distant, previously hidden star adds another data point to our evolving understanding of where our cosmic home begins and ends. There's something almost philosophical about this process of discovery. When a region of the sky is known to contain only a few bright stars, we naturally think of it as relatively empty. When new stars are found there, our mental map of the galaxy fundamentally changes. This shift in perception can influence how astronomers design future surveys and where they choose to focus their attention and resources. Regions once considered low priority can suddenly become areas of intense interest, leading to more detailed studies and often to further discoveries. In this way, the act of finding hidden stars creates a kind of feedback loop, where discovery leads to attention leads to more data, and more data leads to an ever more complete picture of our cosmic neighborhood. This process highlights a recurring theme that runs through all of astronomy and perhaps all of science. Much of what exists in the universe is not immediately obvious to us. It requires specific conditions, specific tools, and often very specific questions to be revealed. The Milky Way, as we see it with our naked eyes, is already a remarkable sight, one that has inspired humans for millennia, but it represents only the surface layer of a much deeper, more complex structure. Infrared observations are beginning to peel back some of that surface, showing us that even in places we thought we knew well, there are still countless layers of complexity waiting to be explored. It's humbling to realize that our familiar night sky is just the visible tip of an enormous cosmic iceberg. There's also something deeply moving about the realization that the stars hidden from us today have been shining for billions of years. They were there long before humans existed, long before Earth took its current form, long before our solar system even began to condense from cosmic dust and gas. They have been part of our galaxy's story all along, contributing to its gravity, following their ancient orbits, helping to shape its evolution, even though we're only now becoming aware of their existence. In that sense, the process of astronomical discovery isn't really about changing the universe at all. It's about changing ourselves, expanding what we notice and what we consider to be part of our cosmic environment. It's about developing new ways of seeing that reveal the hidden richness that surrounds us. When you look up at the night sky tonight and see those familiar patterns of stars, it might be quietly striking to think about what lies behind that pattern. Layered in depth and distance, stretching far beyond what your eyes can detect, there are countless other stars, each with its own billion-year history and its own place in the vast structure of our galaxy. Those hidden stars continue to contribute to the gravity that holds the Milky Way together. They follow their orbital paths through space and time. They influence the shape and continuing evolution of our cosmic home. Their presence, invisible though it may be to us, serves as a reminder that our galaxy's true scale isn't just a matter of measuring how far its brightest, most obvious parts extend into space. Understanding the Milky Way also means recognizing how much of it exists in faint, subtle forms that only become visible when we learn to look in new ways, when we develop new tools and new methods of seeing. As Webb continues to survey familiar regions with its sensitive infrared instruments, it will likely keep finding these quiet additions to our galaxy's map. Each discovery may be small on its own, perhaps just a single previously unknown star or a small cluster, but together they're building up a more extended, more nuanced, and ultimately more accurate outline of the true Milky Way. They're helping us understand that our cosmic home is larger, older, more complex, and more beautiful than we ever imagined, filled with hidden stories written in starlight that we're only just beginning to read. Looking up at the night sky, we see this bright band stretching across the darkness, and for most of human history, that was pretty much our entire concept of the Milky Way. But here's the thing about galaxies: they don't really have edges the way we think of edges. They fade, gradually, like a conversation that trails off rather than ending with a clear goodbye. James Webb has been quietly peering into these faint, dusty regions where our galaxy starts to whisper rather than shout. What it's finding is making astronomers rethink some pretty fundamental ideas about where our cosmic home actually begins and ends. The old textbook description was clean, simple, reassuring, even. A disk of stars, a bulge in the middle, a halo around it all, and then, well, nothing. Empty space between galaxies. But reality, as usual, turns out to be messier than our diagrams. When astronomers started counting stars more carefully in the outer regions of the disk, they kept finding more than they expected. Not bright, obvious stars that grab your attention. These were faint, elderly stars, the kind that are easy to overlook, but they were there, thousands of light years farther out than the models predicted. It's a bit like thinking your neighborhood ends at the last street light, only to discover there are houses scattered in the darkness beyond. The galaxy doesn't just stop, it gradually thins out, and in some directions, it extends much farther than others. This creates a boundary that's more like a shoreline than a wall, with the stellar density ebbing and flowing in ways that resist simple measurement. Webb's infrared vision adds another layer to this picture. It can see stars that emit most of their light at wavelength invisible to our eyes. Suddenly, regions that looked empty, invisible light reveal themselves to be populated with faint, cool stars. The galaxy becomes not just wider, but thicker, more layered, like discovering that what you thought was a thin sheet of paper is actually a complex three-dimensional structure. The Milky Way has this vertical architecture that's often lost in the flat spiral pictures we're used to seeing. There's the thin disk where we live, packed with gas, dust, and young stars, only a few hundred light-years thick. Then there's a thicker disk of older stars, extending thousands of light-years above and below the plane. Surrounding it all is the halo, a roughly spherical cloud of ancient stars that reaches tens, maybe hundreds of thousands of light-years into space. Each of these components tells part of the story. When Webb detects faint stars far above or below the galactic plane, it's like finding forgotten chapters in the galaxy's biography. Some of these stars belong to the thick disk, others to the inner halo. Their ages, their chemical compositions, even the way they move through space, all provide clues about different episodes in the galaxy's long history. The halo itself has become one of the most fascinating and strange parts of this whole structure. For decades, astronomers thought of it as a smooth, spherical envelope around the bright disk. A kind of cosmic fog of old stars and globular clusters. But as surveys became more detailed, that smoothness started breaking apart. Instead of uniformity, the halo is threaded with streams, clumps, and subtle variations in density. These streams are ghost stories written in starlight. Each one is the remnant of a smaller galaxy or star cluster that wandered too close to the Milky Way billions of years ago. Our galaxy's gravity slowly pulled these visitors apart, stretching their stars into long, thin trails that still orbit around us today. Webb's ability to see faint stars makes these streams easier to trace, especially in dusty regions where they were hidden before. Every stream tells the story of an ancient encounter, a gravitational dance that ended with one partner being absorbed into the other. The galaxy we see today isn't a single structure that formed all at once. It's the accumulated result of countless mergers, accretions, and gravitational interactions. Each event added stars, gas, and dark matter to the system, often in uneven ways. This means the Milky Way isn't perfectly symmetrical. In some directions, the halo extends farther. In others, it's more compact. Some regions are rich with streams and substructures, others relatively smooth. When astronomers talk about the galaxy's true scale, they're not describing a simple radius or diameter. They're mapping a complex, lopsided, evolving form that doesn't lend itself to clean boundaries. The word strange fits here, because the more detail we reveal, the less the galaxy resembles the tidy mental image most of us carry around. Consider spiral arms, those graceful curves we see in astronomical photographs, in textbook diagrams. They look like solid, permanent structures wrapping smoothly around the galactic center, but they're not solid at all. They're more like traffic jams in a rotating disk, patterns in the distribution of gas, dust, and young stars. Stars move in and out of these patterns over millions of years. Gas piles up, forms new stars, then drifts away. The arms themselves can shift, split, or fade as the galaxy evolves. When Webb looks at these regions in infrared, it reveals stars hidden behind dust lanes, making the arms appear less like sharp features and more like broad, fuzzy regions with complex internal structure. That fuzziness adds to the sense that the galaxy's shape isn't a clean, well-defined object, but a dynamic pattern in constant motion. It's a bit unsettling, really. We like our cosmic landmarks to be stable, permanent, reliable. Instead, we find ourselves living in something more like a slowly shifting dance of matter and energy. Then there are the galaxy's outermost stars, some with orbits that take them hundreds of thousands of light years from the center. These stars spend most of their time in regions where the Milky Way's gravitational pull is weak, where they're influenced not just by our galaxy, but by the combined gravity of the entire local group of galaxies. In these outer zones, the distinction between belonging to the Milky Way and belonging to the intergalactic environment becomes blurred. The idea of a hard edge starts feeling inappropriate. Instead, the galaxy seems to fade into a broader gravitational landscape where its influence overlaps with that of Andromeda and other nearby systems. The two largest galaxies in our local group are already interacting through their dark matter halos, even though their visible disks are still more than 2 million light-years apart. This interaction is subtle and slow, but it's real. On the largest scales, the Milky Way isn't an isolated island. It's part of a connected system of galaxies gradually moving toward a future merger. From this perspective, the true scale of the Milky Way includes not just its stars and gas, but its role in a larger cosmic neighborhood. Webb's observations of distant galaxies provide useful context here. By studying other spiral galaxies in different environments, astronomers can see how size and structure vary. Some galaxies have very extended halos, others are more compact. Some show clear signs of recent mergers, others appear relatively undisturbed. Our galaxy appears fairly typical in some respects, but it also shows signs of a particularly active history of interactions. The richness of its halo substructures suggests it has absorbed a significant number of smaller galaxies over its lifetime. This helps explain why the halo might be more extended and complex than earlier models assumed. But there's another layer of strangeness here, the relationship between visible matter and dark matter. The stars and gas we can see make up only a small fraction of the galaxy's total mass. The majority exists in the form of dark matter, which doesn't emit or absorb light. The shape of this dark matter halo influences the orbits of stars and satellite galaxies, indirectly shaping the visible structure of the Milky Way. Models suggest the dark matter halo may extend much farther than the region populated by stars. In some estimates, it could reach several 100,000 light-years maybe even close to 1 million light-years, blending into the dark matter halos of neighboring galaxies. If this is true, then the galaxy's gravitational influence extends far beyond the scale defined by its stars alone. Webb doesn't detect dark matter directly, but by providing better data on stellar motions and distributions in the halo, it helps constrain these models. The more accurately astronomers can trace stellar orbits at large distances, the better they can infer the shape and extent of the underlying dark matter. This interplay between the visible and invisible adds a quiet mystery to the galaxy's form. Much of what defines its size is something we cannot see, only feel through its effects. There's also a temporal dimension to consider. The Milky Way we see today is a snapshot in a long process of growth and change. Its size isn't fixed. It has been increasing over time as it absorbs material from its surroundings. In the distant past, the galaxy was smaller, less massive, more chaotic. Over billions of years, it pulled in gas, formed stars, merged with smaller systems, gradually building up the structure we recognize now. The halo is a kind of fossil record of this process. The streams and clumps of stars found there are remains of ancient building blocks. By mapping these features, astronomers can reconstruct a timeline of the galaxy's growth, seeing not just how big it is now, but how it became that big. This historical perspective turns the galaxy into something more like a story than a static object. It has chapters, episodes, turning points written in the motions and compositions of its stars. When Webb reveals a faint stream of stars in the halo, it's not just extending our map, it's uncovering a past event, a moment when another galaxy passed too close and was slowly torn apart. These events have lasting effects on the Milky Way structure, creating ripples in the disk, altering the distribution of stars, contributing to the overall mass and scale. Even the disk itself shows signs of these interactions. Surveys reveal that the Milky Way's disk is warped and rippled, with waves of stars moving up and down, relative to the galactic plane. These waves are thought to result from past encounters with satellite galaxies or dark matter clumps. The galaxy's supposedly flat spiral shape is actually wavy and uneven, adding another layer of complexity to its three-dimensional form. From a distance, if we could somehow see the Milky Way from outside, it might look less like a perfect pinwheel and more like a slightly distorted, layered structure, with faint extensions and asymmetries that hint at its long, active history. All of this contributes to the feeling that the galaxy is not just bigger than we thought, but more intricate. The more closely it's studied, the more it reveals that size isn't just a matter of distance, but of structure, history, interaction. There's a human element in how we perceive this strangeness. We like clear categories, inside and outside, near and far, part of the galaxy and not part of the galaxy. The Milky Way challenges these categories. Its boundaries are fuzzy, its components overlap, its influence extends beyond its visible form. As our instruments improve, we're forced to confront this ambiguity more directly. Webb's contribution isn't that it provides a single definitive measurement of the galaxy's size. It helps reveal the galaxy as a more extended, layered, interconnected system than any simple number can capture. This can feel unsettling, but it can also feel expansive. Instead of living in a neatly bounded cosmic home, we appear to be part of something that blends gradually into a larger environment. A system of galaxies that are themselves part of an even larger cosmic web. From that perspective, the Milky Way isn't just a place. It's a region in a continuous structure of matter and energy that stretches across the universe. Our galaxy exists as something far more fluid than we once imagined. The Milky Way moves, shifts, and breathes in ways that challenge our need for neat categories. Think about it. We've spent decades trying to capture something that refuses to stay still. The disk that holds our solar system isn't the flat, orderly structure we drew in textbooks. It warps and ripples like a sheet hanging on a cosmic clothesline. Some regions bend upward, others dip down, creating waves that stretch across tens of thousands of light years. The large and small Magellanic Clouds, our satellite galaxies, tug at these outer regions as they orbit around us. Their gravitational pull creates disturbances that ripple inward over millions of years. Dark matter adds another layer of complexity here. This invisible substance doesn't distribute itself evenly around our galaxy. Its uneven presence creates subtle forces, pulling different parts of the disk in different directions. The result looks more like a gently flexing surface than the rigid plane we once pictured. Those famous spiral arms we see in every astronomy book, they're not solid structures at all. They're more like traffic jams in space, regions where gas and dust pile up temporarily. Material flows through these patterns, gets compressed, and suddenly bursts into new star formation. The bright young stars make the arms visible for a while, but then they drift away, joining the general population of the disk. This means the arms themselves shift, split, and reform over cosmic time. What we see today might look completely different in 100 million years. Infrared observations reveal stars hiding behind dust lanes, and when we include these hidden populations, the sharp boundaries between arms and empty space start to blur. Everything becomes more of a continuous flow. At the heart of our galaxy sits a supermassive black hole, 4 million times more massive than our Sun. The stars around it don't form a neat spherical bulge, though. They're stretched into a bar-like structure that channels gas inward and influences where new stars can form. This central bar has its own internal complexity, with different stellar populations following different orbital patterns. The halo surrounding everything presents, perhaps, the biggest challenge to our simple models. We used to picture it as a smooth, roughly spherical envelope of old stars and dark matter. Reality is messier. The halo is threaded with streams of stars, remnants of smaller galaxies that our Milky Way consumed over billions of years. These stellar streams loop around the galaxy in long twisted paths, creating a three-dimensional web of overlapping features. Each stream tells a story of cosmic cannibalism, of a smaller system that wandered too close and got torn apart by tidal forces. Together, they make the halo look less like a unified structure and more like a collection of gravitational archaeology. New telescopes keep finding fainter streams, adding detail to this web and making the overall picture more intricate. Gas plays a crucial role that we often overlook. Beyond the cold gas in the disk where stars form, there's a massive reservoir of hot, diffuse gas extending far above and below the galactic plane. This invisible halo of gas acts like a cosmic circulatory system, feeding material back into the disk while carrying away the debris from stellar explosions. When we include all these gas components, cold, warm, hot, ionized, the galaxy becomes a multi-phase system, rather than just a collection of stars. Each phase has its own distribution, its own motions, its own role in the galactic ecosystem. Our perspective matters more than we usually admit. We're stuck inside this system, looking at it from the side, rather than from above. The spiral arms become hard to trace. When you're looking through them, instead of down at them, the halo surrounds us completely, blending into the background of distant galaxies. Everything we think we know about our galaxy's shape comes from this internal viewpoint, pieced together through indirect evidence. Different parts of the galaxy don't even align perfectly with each other. The disk, the central bar, the halo, and the dark matter distribution might each have slightly different centers or orientations. Small offsets between these components can dramatically affect how stars and gas move throughout the system. Past mergers, ongoing interactions with satellite galaxies, even the initial conditions of galaxy formation, all contribute to these misalignments. The broader cosmic environment shapes us too. Our galaxy and Andromeda are gravitationally bound, moving toward an eventual collision in about 4 billion years. Their dark matter halos probably overlap already, creating a shared gravitational space that extends far beyond either galaxy's visible stars. This means our outermost regions aren't entirely our own anymore. There's a hierarchy at work here that connects the very local to the truly cosmic. The disk's shape gets influenced by the halo. The halo gets influenced by our neighbors in the local group. the local group gets influenced by the larger cosmic web of galaxies and dark matter filaments. Each level nests inside the next, creating patterns that repeat across vastly different scales. Motion defines everything in this picture. Our sun races around the galactic center at over 200 kilometers per second. Other stars move faster or slower, depending on their orbital distances. Gas clouds swirl, collapse, and expand in cycles that span millions of years. If we could somehow take a long exposure photograph of the galaxy over deep time, its shape would blur into something completely different from any static image. The spiral pattern would wind and unwind. Streams in the halo would stretch and thin. The warped disk would shift and flex. This dynamic nature means that any shape we assign to the Milky Way captures just a moment in an ongoing process. We're not finding final answers, we're taking snapshots of something that never stops changing. New telescopes add pieces to this evolving puzzle by finding objects that were previously invisible. Faint stars hiding in the halo, obscured regions behind dust lanes, cool objects that only emit infrared light, all contribute to our three-dimensional map. As these observations accumulate, the galaxy's form becomes less like a simple geometric figure and more like a volume filled with structures at different densities and orientations. This creates interesting challenges for how we communicate about our galactic home. Simple diagrams still serve a purpose. They convey the basic concept of a spiral galaxy, but they come with an invisible asterisk now, an acknowledgement that reality is far more complex than any drawing can capture. The balance between clarity and accuracy becomes a philosophical question in itself. Too much detail overwhelms understanding. Too little detail misleads it. We're constantly negotiating this tension between what we know and what we can meaningfully share. Each new discovery opens up questions that connect our local cosmic neighborhood to fundamental processes operating throughout the universe. If the halo contains so many stellar streams, how many smaller galaxies did we absorb during our formation? When did those cosmic meals occur? If the disk stays warped despite billions of years of gravitational settling, what keeps refreshing those distortions? If dark matter doesn't distribute itself symmetrically around our galaxy, what does that tell us about how structure forms on the largest scales? These questions tie the shape of our home to the deepest mysteries in cosmology and galaxy evolution. There's something profound about living inside a system that's still revealing itself to us. The galaxy that once seemed like a familiar backdrop, a fixed stage for cosmic drama, keeps surprising us with its complexity. Its boundaries aren't clearly marked. Its history remains partially hidden. Its future involves dramatic changes we can barely imagine. This ongoing revelation reminds us that even the structures we inhabit most intimately can remain mysterious. We exist within something bigger, more layered, and more dynamic than our first impressions suggested. As observations continue to refine our understanding, the Milky Way becomes less like a static map and more like a story still being written, with us as both characters and readers trying to understand the plot. Our sun isn't sitting still in space, waiting patiently while Earth spins through its seasons. It's actually racing through the galaxy at incredible speeds, carrying all the planets, asteroids, and comets along with it. This journey around the Milky Way takes about 230 million years to complete, just one lap. Think about that for a moment. Since complex life started appearing on our planet, we haven't even finished one trip around our galactic neighborhood. The path our solar system follows isn't a simple circle either. We're bobbing up and down as we orbit, like a cork floating on ocean waves. Sometimes we're above the main disk of the galaxy, sometimes below it. These movements take tens of millions of years, and during each phase we encounter completely different stellar environments. Different densities of stars, different amounts of cosmic dust, different gravitational influences pulling at the edges of our solar system. Recent discoveries show that the Milky Way stretches much farther than we used to think. Its halo, that spherical region surrounding the main disk, extends into distances that boggle the mind. This means our solar system's journey is far more complex than anyone imagined. We're not just cruising through a relatively uniform field of stars. We're navigating through a layered three-dimensional landscape where each region has its own character and history. Far beyond Pluto, our solar system is surrounded by something called the Oort cloud. It's a vast sphere of icy objects, so distant that the sun's gravity barely holds onto them. When our solar system passes through denser regions of the galaxy, the extra gravitational pull can disturb these frozen wanderers. Some get knocked loose and begin the long fall toward the inner planets, eventually becoming the comets that streak across our night sky. The timing isn't random either. As we move through different galactic neighborhoods, the likelihood of cometary visits changes. During some phases of our galactic orbit, Earth might see more comets than usual. During others, fewer. These patterns play out over millions of years, creating subtle rhythms in the solar system's history that we're only beginning to understand. Occasionally, other stars pass relatively close to us on their own galactic journeys. Most of the time, our nearest stellar neighbors are several light years away, far enough that their gravity doesn't affect us much. But every few million years, a star might wander within a light year or so of the Sun. When this happens, it can shake up the outer reaches of our solar system, sending more icy bodies tumbling inward. The galaxy isn't a quiet place, energetically speaking. Somewhere in the Milky Way, a massive star explodes as a supernova roughly every 50 years. Most of these cosmic catastrophes happen far enough away that we barely notice them. But over geological time, there have probably been supernovae close enough to Earth to affect our planet's atmosphere and climate. Some scientists think these distant explosions might have triggered ice ages or mass extinctions in Earth's past. Our position in the galaxy, about 26,000 light-years from the center, places us in what astronomers call the galactic habitable zone. We're far enough from the crowded, violent galactic core to avoid frequent radiation bombardment, but not so far out that we lack the heavier elements needed for rocky planets and complex chemistry. It's a cosmic sweet spot that may have been crucial for life's development on Earth. Every atom in your body, except for hydrogen, was forged inside a star that lived and died before our solar system even existed. When those ancient stars reached the end of their lives, they scattered these elements into space through stellar winds and supernova explosions. The cloud of gas and dust that eventually collapsed to form our sun and planets was already enriched with the products of stellar alchemy: carbon, oxygen, nitrogen, iron, and dozens of other elements essential for life. The distribution of these elements across the galaxy isn't uniform. Regions that have experienced more star formation tend to be richer in heavy elements. Areas that are more isolated, particularly in the outer halo, remain more chemically primitive. Our solar system formed in a region that had just the right mixture, enough heavy elements to build rocky worlds, but not so much that the environment became chaotic. The Milky Way itself is evolving as we travel through it. Spiral arms shift position over hundreds of millions of years. Small satellite galaxies occasionally merge with our own, adding their stars to the mix and creating streams of stellar debris that persist for billions of years. The galaxy we're moving through today is different from the one our solar system inhabited when life first emerged on Earth. This long-term perspective reveals something profound about our cosmic address. We're not just residents of a planet orbiting a star. We're part of a thin disk, embedded within a thick disk, surrounded by an ancient halo, overlapping with neighboring galactic halos, all of which belong to a local group of galaxies that itself sits within a vast filament of cosmic structure. Each layer adds context to our existence. The search for life elsewhere in the galaxy takes on new dimensions when we consider these environmental factors. Some regions might be too violent for complex life, with frequent supernova explosions sterilizing nearby worlds. Other areas might lack the chemical diversity needed for biology. Still others might be so isolated that planetary systems never form in the first place. Our solar system's relatively stable journey through a moderate stellar neighborhood starts to look less like an accident and more like a requirement. The conditions that allowed Earth to develop and maintain life for billions of years may depend partly on the galactic environment we've been moving through. It's a reminder that habitability isn't just about having the right kind of star and planet, it's also about occupying the right kind of galactic real estate. Looking ahead, the Milky Way and its nearest large neighbor, the Andromeda Galaxy, are slowly approaching each other. In about 4 billion years, they'll begin to merge, completely reshaping both galaxies in the process. The solar system will survive this collision, but its environment will change dramatically. Our descendants, if any exist, will inhabit a very different galaxy, one born from the merger of two ancient spiral systems. There's something both humbling and comforting about understanding our place in this vast dynamic structure. On human timescales, the galaxy seems eternal and unchanging. On cosmic timescales, everything is in motion, evolving, transforming. We're part of an ongoing story that began billions of years ago and will continue for billions more. The realization that our galaxy is larger and more complex than we thought doesn't diminish our significance. It enriches our understanding of the context we exist within. Every sunrise, every season, every generation of life on Earth unfolds against the backdrop of this grand cosmic journey. We're not separate from the galaxy. We're part of it, products of its chemistry and passengers on its long voyage through space and time. The galaxy we call home exists as a constantly shifting entity, with billions of stars following their own orbital paths around a central point we can never directly see. Unlike the maps we create of our planet, where mountains stay put and cities remain in place, mapping the Milky Way presents a challenge that defies our usual understanding of how cartography works. Every observation we make is essentially time travel, a glimpse into the past that varies depending on how far we're looking. When astronomers point their telescopes toward a star that sits 1,000 light-years away, they're witnessing that star as it appeared a millennium ago. The light we see left that distant sun when medieval castles were being built on Earth. This means our galactic map isn't really a snapshot of any single moment, but rather a collection of different time periods, all stitched together into something we hope resembles the present state of things. The center of our galaxy, located roughly 26,000 light-years from our solar system, appears to us as it existed when early humans were first learning to cultivate crops. That's an almost incomprehensible span of time, yet in cosmic terms, it represents just a brief moment in the galaxy's 4 billion-year history. The light carrying information about that central region has been traveling through space for longer than recorded human history, crossing vast emptiness to eventually strike the mirrors of our telescopes. This relationship between distance and time creates fascinating complications when scientists try to understand galactic structure. Consider the spiral arms that give our galaxy its distinctive shape. When we observe these arms in different directions, we're seeing them at slightly different periods in their evolution. The patterns shift and change as gas clouds move through them, as new stars form and die, as gravitational forces reshape the distribution of matter. What appears to be a single coherent structure is actually a compilation of many different moments frozen in light. Star streams in the outer halo present an even more complex puzzle. These long, thin structures form when smaller galaxies or star clusters get torn apart by the Milky Way's gravity, leaving behind trails of stars that follow similar orbits. When we observe such a stream, the stars closer to us appear as they were more recently, while the more distant parts show us further into the past. The stream itself is moving and stretching during this time, so the shape we see doesn't correspond to any single moment of its existence. It's a time-smeared version of reality, like a photograph taken with a slow shutter speed. The tools astronomers use to study our galaxy each have their own strengths and limitations. Parallax measurements can provide incredibly precise distances, but only for nearby stars within a few thousand light-years. Beyond that range, scientists must rely on more indirect methods, with greater uncertainty. Standard candles, objects with known brightness, help estimate distances to farther regions, but these measurements come with larger error bars and more assumptions built into the calculations. Different parts of the galaxy require different approaches entirely. The dense, dusty regions near the galactic center block visible light, making infrared observations essential for peering through the cosmic haze. The sparse outer halo contains so few stars that each new detection carries significant weight in determining the galaxy's overall structure and extent. When a powerful telescope like James Webb spots a previously unknown star in these remote regions, it can shift our understanding of where the Milky Way's boundary actually lies. Our position inside the galaxy creates its own set of observational challenges. We sit roughly halfway between the center and the edge, embedded within the galactic disk, like passengers trying to map a train from inside one of the cars. This internal perspective means some parts of our galaxy will always be easier to study than others. The far side of the disk, for instance, remains partially hidden behind a central bulge, its light filtered through layers of dust and gas before reaching our instruments. The very concept of galactic boundaries becomes philosophically interesting when examined closely. Unlike countries with defined borders or cities with clear limits, the Milky Way fades gradually into the surrounding space. Its stellar density decreases slowly with distance. Its gravitational influence overlaps with neighboring galaxies. Its dark matter halo extends far beyond the visible stars. Astronomers must make somewhat arbitrary decisions about where to draw the line between what belongs to our galaxy and what doesn't. These definitional choices mean that when new observations suggest the Milky Way is larger than previously thought, what's often changing isn't the physical galaxy itself, but our understanding of which components to emphasize. Include more of the stellar halo, and the galaxy grows. Factor in the extended dark matter distribution, and it becomes larger still. Each layer tells a different story about the same cosmic structure. Modern galactic cartography relies on surveys that catalogue millions or billions of individual stars. The sheer scale of this data collection would have been unimaginable just decades ago. Missions like Gaia measure the positions and motions of stars with extraordinary precision, creating a dynamic map that shows not just where stars are, but where they're going. This adds another dimension to our understanding, to our understanding, to our understanding, to our understanding. Yet even these comprehensive surveys have their blind spots. Gaia excels at detecting bright stars in relatively clear regions of space, but struggles with very faint objects or areas heavy with cosmic dust. James Webb can peer through that dust with its infrared vision and spot incredibly distant dim stars, but its field of view covers only small patches of sky at a time. Each instrument contributes unique pieces to the puzzle, and combining these pieces requires careful calibration and statistical modeling. Selection effects add another layer of complexity to galactic mapping. Every survey has limits on what it can detect, biases built into the very process of observation. A survey that only spots stars brighter than a certain threshold will naturally miss the fainter population, potentially skewing our understanding of how stars are distributed throughout the galaxy. Correcting for these effects requires assumptions about the underlying stellar populations, assumptions that themselves evolve as new data becomes available. The process of mapping our galaxy has become a continuous conversation between observation and theory. New detections lead to refined models, which suggest new places to look, which yield fresh discoveries that require further theoretical updates. It's an ongoing cycle that never quite reaches a final, definitive answer. In some ways, this seems appropriate for a galaxy that is itself never finished, never static, always in the process of forming new stars and interacting with its cosmic neighbors. There's something profound about the fact that we, as residents of this galaxy, are engaged in the project of understanding our own cosmic home. We're both inside the system we're trying to map and dependent on that system for our very existence. The heavy elements in our bodies were forged in the nuclear furnaces of earlier stellar generations, scattered into space when those stars died, and later incorporated into the gas cloud that would eventually form our solar system. Time operates on such different scales in this galactic context that it challenges our usual ways of thinking about change and permanence. From our perspective, the major structures of the Milky Way seemed eternal and unchanging. The spiral arms appear fixed, the central bulge looks permanent, the overall architecture seems stable. Yet when we consider timescales of millions or billions of years, everything is in motion, everything is temporary, everything is part of an ongoing story of cosmic evolution. The dark matter that makes up most of the galaxy's mass remains largely invisible and mysterious, detectable only through its gravitational effects on the stars and gas we can observe. This invisible component may extend the galaxy's influence far beyond its visible boundaries, creating a vast halo of unseen matter that we're only beginning to understand. The true edge of the Milky Way might lie much farther out than we currently realize, in regions where dark matter finally becomes too sparse to bind to our galaxy's gravitational well. As our instruments become more sensitive and our surveys more comprehensive, we continue to discover new streams of stars in the outer halo, evidence of small galaxies that our own Milky Way has consumed over billions of years. These stellar streams are like archaeological artifacts, preserving information about galactic interactions that occurred long before Earth formed. They remind us that our galaxy didn't always exist in its current form, but grew through countless mergers and accretions over cosmic time. The challenge of creating accurate galactic maps reflects broader themes in how we understand complex systems. We work with incomplete information, make reasonable approximations, and constantly refine our models as new evidence emerges. The maps we create are always provisional, always open to revision, always shaped by the limitations of our current tools and techniques. Yet, these maps also represent genuine progress in understanding, each iteration bringing us closer to a more complete picture of our cosmic neighborhood. Our home galaxy sits in a peculiar position when you think about the vast cosmic neighborhood we're part of. The Milky Way has always been this middle child of the universe, never quite the biggest, never quite the smallest. It's like finding yourself perfectly average in a crowd, which is both comforting and slightly mysterious when you really consider it. When astronomers look out into space, they see galaxies that dwarf our own, massive elliptical systems that dominate entire regions of the universe. These giants are smooth, rounded collections of ancient stars, often sitting at the hearts of galaxy clusters like cosmic metropolises. Then there are the tiny dwarf galaxies, fragile little systems that drift through space or orbit larger galaxies, like cosmic suburbs. The Milky Way has long been considered a fairly standard spiral galaxy. It has the classic disk shape, the sweeping arms, the central bulge. Nothing too extraordinary, nothing too unusual, but recent observations are starting to paint a more complex picture. One that makes you wonder what typical really means when we're talking about something as vast as a galaxy. Comparing galaxies is a bit like comparing cities. You can look at population, you can look at size, you can look at architecture. Galaxies come in spirals like ours, with their elegant, rotating disks and star-forming regions. Others are ellipticals, more like cosmic footballs filled with older, redder stars. Then you have the irregulars, galaxies that look like they've been through some kind of cosmic accident, shaped by collisions and internal chaos. Even within spiral galaxies, the variety is stunning. Some have arms wound tight, like a spring. Others have loose, sweeping curves. Some are actively forming new stars at a rapid pace. Others have settled into a more sedate middle age. The Milky Way seemed to fit comfortably somewhere in the middle of this spectrum, about 100,000 light-years across, similar in scale to our neighbor Andromeda. But here's where things get interesting. Most of what makes up a galaxy isn't actually the stars you can see. It's dark matter, this invisible substance that outweighs everything else by a factor of 5 to 1. The dark matter forms a halo around each galaxy, and this halo determines how the galaxy behaves, how it interacts with neighbors, how it captures smaller systems. Measuring the Milky Way's dark matter halo is incredibly difficult. You're trying to weigh something invisible using the gravitational effects it has on things you can barely see. As astronomers get better at this cosmic weighing game, they're finding that our galaxy might be more massive than they thought. This changes everything about how we fit into the galactic hierarchy. If the Milky Way is more massive, then its gravitational reach extends further. It can influence more of the space around it, capture more satellite galaxies, interact more strongly with neighbors, like Andromeda. The two largest galaxies in our local group might be more evenly matched than anyone realized. When they eventually collide in about 4.5 billion years, it won't be a case of a small galaxy being swallowed by a large one. It'll be more like two heavyweight boxers meeting in the ring. This future merger, sometimes playfully called Milky Way, will create something entirely new. The collision will scramble the neat spiral patterns of both galaxies, flinging stars into new orbits, triggering bursts of star formation, and eventually settling into a single, larger elliptical galaxy. It's a reminder that even on cosmic scales, nothing stays the same forever. Looking beyond our local neighborhood, surveys of thousands of other galaxies reveal that spiral systems like the Milky Way are fairly common. They tend to live in small groups rather than the dense cores of galaxy clusters, and this environment matters more than you might think. In clusters, galaxies are subjected to violent interactions and hot, dense gas that can strip away their own material and shut down star formation. Group galaxies like ours get to keep their gas longer and continue forming stars over extended periods. What's becoming clear is that the Milky Way's halo is incredibly structured, filled with streams of stars and remnants of smaller galaxies that were consumed over billions of years. This isn't unique. Many large galaxies show similar features. But because we're inside the Milky Way, we can study these structures in incredible detail, star by star, stream by stream. This proximity gives us a kind of cosmic laboratory. We can trace chemical compositions of individual stars, map the three-dimensional structure of stellar streams, and follow the orbits of satellite galaxies with precision that's impossible for distant systems. The Milky Way becomes a reference point, a nearby example that helps interpret what we see in galaxies millions of light years away. The disk of our galaxy appears fairly typical too. It's not a starburst system where stars are forming at an exceptional rate, nor is it a quiet, aging galaxy where star formation has mostly stopped. It sits in the middle, forming a few new stars each year, a pace that seems common among similar systems. But as mapping improves, the disk appears to extend further than once thought, making our galaxy perhaps more expansive than the simple, tidy picture often presented. Chemical composition tells another story about galactic evolution. Stars near the center and in the thin disk are generally richer in heavy elements, while stars in the halo and thick disk are more primitive, formed when the universe was younger and had fewer heavy elements floating around. This pattern appears in many spiral galaxies, but we can study it in our own galaxy with a resolution that's impossible anywhere else. If you could somehow step outside and look at the Milky Way from a distance, it would probably look like many of the spiral galaxies you see in deep space photographs. A bright, barred center, elegant spiral arms, and a faint extended halo. What would be harder to see are the subtle features, the streams and shells of stars that hint at our galaxy's complex history of mergers and interactions. Our local group is a relatively quiet neighborhood compared to massive galaxy clusters. In clusters like Virgo, thousands of galaxies are packed together, experiencing frequent high-speed encounters and the influence of hot gas that fills the space between them. Our environment is more gradual, allowing galaxies to maintain their disks and continue forming stars over long periods. This peaceful setting has allowed the Milky Way to grow through mergers with smaller galaxies without being subjected to the disruptive forces present in dense clusters. The complex structure we see in the halo is partly a product of this environment, a steady accumulation of smaller systems over cosmic time. Looking deeper into the universe means looking back in time, and distant galaxies show us how galaxy formation has changed over cosmic history. In the early universe, galaxies were generally smaller, more irregular, and more actively forming stars. Mergers were more common and structures were less settled. As the universe aged, galaxies grew, disks formed, and star formation rates declined. The Milky Way's extended halo and layered structure represent the outcome of this long process. It's a mature galaxy that has had billions of years to assemble its mass and accumulate its complex halo of stars and dark matter. In this context, our galaxy serves as an example of what a large spiral can look like in the later stages of cosmic history. The satellite galaxies orbiting the Milky Way provide another point of comparison. We have dozens of known dwarf companions, some bright and well-studied, others so faint they're difficult to detect. Recent surveys continue to discover new ultra-faint systems, and this population is an important test of cosmological models, particularly those related to dark matter. Some models predict that large galaxies should be surrounded by many small dark matter clumps, some of which host stars and become visible as dwarf galaxies. The number and distribution of satellites around the Milky Way are compared to similar systems around other galaxies to test these predictions. As we map the halo in greater detail, it becomes possible to better understand how these satellites have interacted with the main galaxy over time. If the Milky Way's halo is particularly rich in substructure, it may indicate a more active merger history than average, or it may simply show that similar structures exist around other galaxies but are harder to detect at great distances. The Milky Way's gravitational influence is more modest than some galaxies, particularly the massive ellipticals in clusters that shape the motion of many nearby systems. Our influence is limited largely to the local group, but within that group we play a significant role. The extended dark matter halo helps define the gravitational landscape that smaller galaxies move through. Comparing the Milky Way to other galaxies isn't really about ranking it on a scale of size or mass. It's about understanding it as one example in a diverse population of systems, each shaped by its own history and environment. The realization that our galaxy is wider, deeper, and more layered than once thought doesn't necessarily make it exceptional. It makes it more clearly part of a general pattern where large galaxies grow through mergers and develop complex halos. What changes is the level of detail in which this pattern can be studied. Because we're inside the Milky Way, we can observe it with unprecedented precision. This provides a kind of ground truth for models of galaxy formation that are applied throughout the universe. Our galaxy becomes both ordinary in its basic type and scale, and special in its proximity and the level of detail it offers. This creates a bridge between the local and the cosmic. The Milky Way becomes a lens through which we can better understand the broader population of galaxies. At the same time, comparisons with other galaxies help put our home in context, showing it as neither uniquely special nor entirely unremarkable, but as one example in a vast spectrum of galactic forms, shaped by its own particular history, but governed by the same physical processes that operate throughout the universe. When we peer into the cosmos, searching for answers about our galactic neighborhood, we encounter a profound puzzle. The Milky Way, our cosmic home for billions of years, reveals itself to be far stranger and far more elusive than the spiral of stars we imagine when we look up at the night sky. Most people picture our galaxy as a collection of bright points, glowing stellar nurseries, and dark ribbons of cosmic dust. These visible components paint the familiar portrait we see in textbooks and documentaries. But here's something that might surprise you. All of these luminous features, every star we can see, every glowing cloud of gas, represents only a tiny fraction of what actually makes up the Milky Way. The vast majority of our galaxy exists in a form that doesn't interact with light at all. This invisible component, what scientists call dark matter, surrounds and permeates every visible structure we know about. It doesn't glow, it doesn't absorb starlight, it doesn't reflect anything back to our instruments. The only way we know it's there comes from watching how it bends space itself, creating gravitational effects that pull on the things we can observe. Stars orbit the galactic center much faster than they should, if only the visible matter were holding them in place. Small satellite galaxies dance around the Milky Way along paths that suggest something far more massive than stars and gas alone is guiding their motion. Streams of ancient stars stretch across the galactic halo, their curves and distortions revealing the shape of an unseen mass distribution that dwarfs everything we can actually see. This dark matter forms what astronomers call a halo, a vast spherical envelope that may extend several times farther than the visible galaxy. Think about that for a moment. The Milky Way we know, with all its spiral arms and stellar populations, sits like a small bright nucleus inside this much larger, completely invisible structure. It's as if we've been studying the tip of an iceberg, while the vast bulk of our cosmic home remained hidden beneath the surface. Even with the most advanced telescopes, this dark halo remains largely mysterious. Scientists can estimate its size and mass, but these calculations come with enormous uncertainties. Different models can fit the same observations, leading to wildly different conclusions about how this invisible matter is distributed through space. Some theories suggest the halo is relatively smooth, a roughly spherical cloud of exotic particles. Others propose it's filled with smaller clumps and concentrations, a network of dark substructures that could influence the motion of stars in subtle but detectable ways. A few stellar streams show signs of having been disturbed by something unseen, possibly a dark matter clump passing nearby like a ghost ship in the cosmic ocean, but these hints remain frustratingly incomplete. Most of our galaxy's true architecture exists only in theoretical models, not in direct observation. We're like archaeologists trying to reconstruct an ancient city from a handful of pottery shards, knowing that the vast majority of the structure lies buried beyond our reach. As astronomers push their surveys deeper into space, discovering fainter and more distant stars, the apparent boundary of the Milky Way keeps expanding outward. But at these extreme distances, the very concept of what belongs to our galaxy becomes unclear. The gravitational influence of neighboring galaxies, especially the approaching Andromeda, starts to compete with the Milky Way's pull, creating transition zones where the idea of inside and outside loses its meaning. There will always be stars too faint to detect, regions too sparse to map completely. Beyond them lies a realm that may still be connected to our galaxy through dark matter, but contains little or no visible evidence of that connection. These outer territories exist in a kind of observational twilight, neither fully accessible nor entirely theoretical. The galaxy's past presents another layer of hidden complexity. The Milky Way formed more than 13 billion years ago, when the universe was younger, denser, and very different from today. Those early epochs involved the collapse of primordial gas and dark matter into the first small structures, which then merged and grew into larger systems over cosmic time. None of the direct evidence from that ancient era survives in a form we can easily observe. The oldest stars carry chemical fingerprints of those early conditions, but they're like messages in bottles, indirect witnesses to events we can never see directly. Their compositions tell us about earlier generations of stars that lived and died before them, but the galaxy's infancy remains hidden behind billions of years of subsequent evolution. Between the stars themselves lies another, largely invisible component: the interstellar medium. This complex mixture includes everything from cold, dense molecular clouds to hot, diffuse plasma scattered throughout the galactic halo. Some of this material can be detected through radio waves or infrared emission, but vast regions remain poorly mapped, especially the hot gas that forms a tenuous envelope around the entire galaxy. This hot halo plays a crucial role in galactic evolution, acting as both a reservoir of material that can cool and fall back into the star-forming disk, and as a repository for energy and matter ejected by stellar explosions. Despite its importance, much of this gas exists at such low densities that it hovers at the edge of detectability, another major component of galactic structure existing in observational shadow. Even within well-studied regions, there are always finer details that escape detection. In star-forming clouds, the processes that create individual stars and planetary systems happen on scales that push the limits of even our most powerful instruments. There will always be smaller motions, more subtle interactions, tinier structures that lie below the threshold of current technology. The galaxy also contains phenomena that don't produce light in any conventional sense. Gravitational waves ripple through space when massive objects like black holes merge, carrying information about violent events that leave no electromagnetic signature. These distortions in space-time itself pass through our solar system constantly, but they're detected by specialized instruments that measure incredibly tiny changes in distance, not by traditional telescopes. Similarly, neutrinos stream through the galaxy and through our own bodies, nearly massless particles produced in nuclear reactions and stellar explosions. They carry information about processes deep inside stars that can't be observed any other way, adding another layer of galactic activity that exists outside the familiar realm of light-based astronomy. These alternative messengers suggest that our galaxy is far richer and more complex than what appears in even the most detailed images. They hint at aspects of the Milky Way that are accessible only through entirely different kinds of observation, many of which are still in their technological infancy. There's also the unsettling possibility that some parts of our galaxy are hidden not just from our instruments, but from our current understanding entirely. Dark matter itself exemplifies this challenge. We know it exists because of its gravitational effects, but we have no idea what it's actually made of. The theories range from exotic subatomic particles to modifications of gravity itself, each possibility carrying different implications for how we interpret galactic structure. If dark matter turns out to interact with itself, or with ordinary matter in unexpected ways, it could completely change our picture of how the galactic halo formed and how it continues to evolve. These uncertainties add yet another layer of invisibility to our cosmic home, one rooted in the limits of current physics rather than observational technology. History suggests we should expect surprises. Astronomers have repeatedly discovered entirely new classes of objects, pulsars, quasars, gamma-ray bursts, phenomena that weren't predicted by existing theories. It's entirely possible that the Milky Way contains populations of objects we haven't yet recognized, either because they're rare, faint, or emit energy in ways we haven't thoroughly explored. New instruments expand the range of what can be observed, but they also reveal new forms of invisibility. Each advance in sensitivity or spectral coverage brings previously hidden structures into view, while simultaneously highlighting how much more remains beyond the current observational horizon. The future itself represents another category of the unseen. Galactic structure will change over cosmic time as stars move, form, and die, as satellite galaxies merge, as the dark matter halo evolves under the influence of neighboring systems. We can model these processes and make predictions, but we cannot observe them directly, at least not on the timescales that matter for galactic evolution. The galaxy we map today captures only one moment in a long sequence of forms. Past versions of the Milky Way are lost to time. Future versions exist only in computer simulations. In this sense, most of our galaxy's timeline remains permanently invisible, accessible only through theoretical reconstruction and extrapolation. Perhaps there's something deeper at work here, something that goes beyond the technical challenges of observation. Every map, every model, every image represents a translation of reality into forms our minds can grasp. The Milky Way as it actually exists is a four-dimensional system of matter, energy and curved space-time, evolving over billions of years. The Milky Way as it exists in our understanding is necessarily a simplified version of that reality, shaped by the limitations of human perception, instrumental capability, and theoretical framework. What we cannot see includes not just physical components like dark matter and tenuous gas, but also aspects of galactic behavior that don't fit neatly into our current conceptual categories. Science advances by gradually converting the invisible into the visible, sometimes literally through new observational techniques, sometimes conceptually through theoretical breakthroughs that allow familiar data to be interpreted in revolutionary ways. This transformation has happened repeatedly throughout astronomical history. Planets were once merely wandering points of light. Other galaxies were once thought to be glowing clouds within our own. Dark matter began as an unexpected anomaly in measurements of galactic rotation curves. Each shift in understanding expanded the known universe, while simultaneously revealing new categories of the unknown. Today's Milky Way is already far more detailed and complex than astronomers could have imagined a century ago. Yet by most reasonable measures, the majority of it remains unseen, unmapped, or poorly understood. This isn't necessarily a failure of science so much as a reflection of scale and complexity. When a system spans hundreds of thousands of light years and includes components that barely interact with the electromagnetic radiation we use for most observations, some degree of invisibility becomes inevitable. What changes over time is not the existence of these hidden aspects, but our ability to infer, model, and partially understand them. As advanced instruments continue to refine the visible picture of our galaxy, they also sharpen the contrast with what remains invisible. Each new discovery illuminates not only previously hidden structures, but also highlights the vast territories that still lie beyond direct observation. This ongoing tension between the seen and unseen drives much of modern galactic astronomy. It keeps our maps perpetually unfinished, our fundamental questions open, and our sense of cosmic scale flexible rather than fixed. The Milky Way remains, even in our age of space telescopes and comprehensive surveys, something more than a completely known object. It exists as a system, with both a visible face and a hidden dimension, a structure that demands not just measurement and calculation, but also imagination and intellectual humility. As the boundaries of observation continue to expand outward and inward, the persistent presence of the unobservable serves as a reminder that our story of galactic citizenship is still very much being written. The night sky above us tells a story that keeps changing as we learn more about what lies beyond those twinkling points of light. Every time astronomers peer deeper into space, they discover that our galaxy, the Milky Way, is far more complex than we ever imagined. Think about how your sense of home might shift if you suddenly realized your neighborhood was 10 times larger than you thought. That's essentially what's happened with our understanding of where we live in the cosmos. The Milky Way isn't just a neat spiral of stars spinning in space. It's more like a vast layered system that stretches much farther than anyone expected. Stars, gas, dust, and invisible dark matter all swirl together in patterns that blur the edges of what we call our galaxy. The boundaries aren't sharp lines. They fade gradually into the emptiness beyond, like watercolor paint bleeding into wet paper. Our solar system moves through this cosmic structure, but it's not traveling through the tidy, well-defined home that earlier generations of astronomers described. Instead, we're sailing through something that's both familiar in its basic shape and mysterious in its true extent. This creates an interesting problem. What does it mean to be inside something when its edges are so fuzzy? When scientists thought the galaxy was mainly a disk of stars with a modest halo around it, the question seemed straightforward. You were either in the disk, in the halo, or somewhere else entirely. But as that halo grows larger and more complex in our measurements, the clarity dissolves. We're definitely well within the main disk of stars, far from the most distant parts of the galaxy, yet we're still influenced by structures we can't even see directly. The dark matter that makes up most of our galaxy's mass creates an invisible envelope around everything. This unseen material shapes the path our sun takes through space, even though it gives off no light at all. Being inside the Milky Way now means being part of a structure whose most important features remain completely invisible to our eyes. The center of our galaxy has also become more interesting as we've learned more about it. For decades, it served as a simple reference point, the hub from which everything else was measured. But recent discoveries reveal a bar-shaped structure in the inner regions, with complex flows of gas moving through intricate patterns of stars. The galactic center isn't just a fixed anchor point anymore. It's a dynamic region in its own right. Our relationship to this center depends not just on distance, but on how the entire galaxy's mass, including all that invisible dark matter, influences our sun's orbit through space. There's also the matter of time to consider. The Milky Way we inhabit today isn't the same galaxy that existed when our solar system formed over 4.5 billion years ago. Galaxies grow, merge with other galaxies, and change dramatically over such vast periods. The region where our sun was born was probably already enriched with heavy elements from earlier generations of stars, but that birth region itself has likely moved, warped, and shifted as the whole galaxy evolved around it. This makes the idea of a permanent home address in space rather meaningless. Our location isn't just a point in space. It's a point along a very long journey through an ever-changing cosmic landscape. When our sun first ignited, entire regions of the galaxy's outer halo may not have existed yet. Streams of stars from ancient galactic mergers hadn't formed because those mergers were still in the future. Smaller satellite galaxies that have since been absorbed were still independent systems orbiting nearby. All of this means we're moving through a galaxy that's more extended and complex than the one we started in. Being part of the Milky Way isn't a static condition. It's more like playing a role in an ongoing story that spans billions of years. The galaxy isn't a container holding us in place. It's a system that shapes us while being shaped by the movement of all its parts. This creates a fascinating feedback loop between the cosmic and the local. When astronomers compare our galaxy to others at different stages of development, They see that the Milky Way's current form represents just one moment in a spectrum of possible structures. Some galaxies are compact and dense, others spread out and thin. Some actively birth new stars, others have gone quiet. Our galaxy, with its newly understood scale and complexity, fits into a category of large, mature spiral galaxies with rich merger histories and extended halos. This makes our position both ordinary and unique at the same time. Ordinary because we live in a galaxy that follows the same physical laws as countless others across the universe. Unique because the specific details of our galaxy's history, its particular pattern of mergers, its current structure, are unlike anywhere else. The boundaries we're used to in everyday life simply don't apply at galactic scales. A room ends at walls, a country at borders, a planet at its atmosphere. But the Milky Way fades out gradually, in all directions. Its dark matter halo extends invisibly, its gravitational influence overlapping with nearby galaxies. This means being inside our galaxy is more like being part of a region that blends into something larger, rather than being contained within sharp borders. Instead of separate, isolated objects, we get a picture of overlapping systems, each embedded within larger contexts. Our solar system sits within the Milky Way, which sits within the local group of galaxies, which sits within the filament of the cosmic web. Each level doesn't end cleanly, it blends into the next, creating a continuous structure stretching in all directions. This layered embedding can actually feel more connected than the old idea of nested boxes. Rather than being a tiny point in separate containers, we become part of an unbroken structure that extends across the observable universe. The immediate scales still matter most for life as we know it. Earth, our solar system, and nearby stars create the environment where biology can flourish. But now these local environments exist within a much broader, more connected framework. Understanding the galaxy's true size and structure also helps predict its future. The eventual collision with the Andromeda galaxy isn't just speculation anymore, it's a predictable consequence of the gravitational landscape both galaxies inhabit. From our perspective, being inside the Milky Way is temporary, in the sense that the galaxy itself will eventually merge into something larger. We won't leave the galaxy, but the galaxy will transform around us, absorbing Andromeda and becoming an entirely new type of system. This long-term view suggests that even the largest structures we can meaningfully discuss aren't permanent. They evolve, combine, and transform over cosmic time, always in the process of becoming something else. Each new discovery about our galaxy's structure makes it feel less like a solved puzzle and more like an open field of investigation. Every faint stream of stars, every distant cluster, every refined model of dark matter distribution adds layers to our understanding. This creates a kind of intellectual humility. Even our own galaxy, the one we live inside, remains incompletely mapped and imperfectly understood. Yet this also emphasizes our capacity for knowledge to grow through observation, theory, and technological advancement. The expanding picture results from generations of collaborative work spanning cultures and continents. As new data arrives from advanced telescopes, researchers around the world analyze, debate, and interpret the findings together. Our place inside this expanding understanding includes both our physical position in space and our intellectual position within a global network of scientific inquiry. Both forms of belonging connect local experience to cosmic scales. Modern surveys reveal that large spiral galaxies like ours, with extended halos and complex merger histories, represent common outcomes of cosmic evolution. This suggests our environment isn't rare or exotic, at least in broad terms. Yet the specific details of our galaxy's story, the timing of its mergers, the distribution of its dark matter, the patterns of star formation, remain absolutely unique. This combination of the general and the specific gives our sense of place its rich texture. Understanding galactic structure also helps frame the search for life elsewhere. Different regions offer different conditions, some crowded and energetic, others quiet and stable. Our location in a relatively calm part of the disk appears favorable for complex life. As the galactic map grows more detailed, scientists can identify other regions sharing similar characteristics. This doesn't guarantee life exists elsewhere, but it provides context for thinking about where conditions might prove more or less hospitable. There's an aesthetic element to this broader picture as well. A galaxy that fades gradually into larger structures, layered and connected rather than sharply bounded, suggests a kind of cosmic continuity. The universe emerges not as separate objects, but as networks of systems blending into one another. Inside and outside become relative terms, rather than absolute categories, creating nested relationships where each level serves as both container and contained. This nested structure offers a way of thinking about scale, without creating hierarchies of importance. Earth matters for human life, the solar system for planetary dynamics, the galaxy for stellar environments, the cosmic web for galactic distribution. All coexist without any single scale defining the others. For individuals learning about these scales, there's often a moment of disorientation when familiar ideas about distance and size no longer fit. This usually gives way to adjustment, where new scales become integrated into how we imagine the universe. This personal process mirrors the larger scientific journey. Both involve taking in new information, letting it challenge existing models, then weaving it into more complex understanding. Moving from simple pictures of spiral galaxies to views of layered evolving systems with fuzzy boundaries and deep histories transforms how we think about our place. We shift from being a point on a simple map to occupying a location within a story stretching across space and time. As this story continues unfolding, more revisions and extensions will undoubtedly emerge, each subtly shifting our understanding of the galaxy and our position within it. This ongoing process doesn't lead toward final answers, but toward deeper, more textured connections. Within this vast evolving structure, our sense of place becomes not just about where we are, but about how we understanding where we are, and how that understanding grows alongside our ever-expanding map of the cosmic neighborhood we call home. The Milky Way stretches much farther than we once thought, but this discovery doesn't change what you see when you look up. The same patterns of stars hang overhead, the same soft band of light curves across dark skies. What has changed is the meaning behind that view. Each point of light now represents something far more vast, far more connected than earlier generations could imagine. Our galaxy extends well beyond the bright disk we're familiar with. It fades gradually into what astronomers call the stellar halo, a region where ancient stars drift in wide, lonely orbits. These stars are old, some of the first to form when the Milky Way was young. They carry stories of cosmic collisions, of smaller galaxies that were absorbed billions of years ago. Their scattered paths trace the history of our galaxy's growth. Dark matter plays a role in all of this, though it never announces itself directly. This invisible mass outweighs everything we can see. It shapes the motion of stars, influences the structure of the galaxy, creates a kind of scaffolding that holds everything together. Without it, the Milky Way would look completely different. Stars would move in chaotic patterns. The spiral arms would unravel. The orderly rotation we observe today simply wouldn't exist. The Earth sits within this vast structure, orbiting a star that moves through space at incredible speeds. Our Sun completes one orbit around the galactic center every 230 million years. That's a cosmic year. A time span so long that the last time we were in this same position, dinosaurs hadn't yet appeared on Earth. The motion is smooth, steady, predictable. We're passengers on a journey we never feel. From our perspective, nothing seems to move at all. The constellations appear fixed, unchanging across human lifetimes. This stability exists because of the enormous scales involved. Distances between stars are so vast that even rapid motion becomes imperceptible. It's like watching a distant airplane, how it seems to crawl across the sky despite traveling at hundreds of miles per hour. The galaxy's extended halo contains streams of stars, remnants of ancient cosmic meals. When the Milky Way encounters a smaller galaxy, gravity slowly pulls it apart. The process takes hundreds of millions of years. Stars get stripped away, one by one, forming long trails that wrap around our galaxy like ribbons. These stellar streams are still being discovered today. ghostly evidence of events that happened long before the sun existed. Some regions of the halo are incredibly sparse. A single star might be isolated in a volume of space larger than our entire local stellar neighborhood. These stars experience a kind of cosmic loneliness that's hard to imagine. They have no nearby companions, no stellar clusters, no dense spiral arms full of activity. They simply orbit in the vast emptiness between the galaxy's bright disk and its invisible dark matter boundary. The dark matter itself extends even farther out, creating what scientists call the virial radius. This marks the edge of the galaxy's gravitational influence, the point where its pull becomes too weak to hold onto new material. At this distance, the Milky Way finally fades into the larger cosmic web, that vast network of matter and energy that connects all galaxies across the universe. Understanding these scales can shift perspective in subtle ways. The Earth rotates every 24 hours, creating day and night. It orbits the Sun once per year, defining seasons. The Moon circles monthly, pulling tides across oceans. All of these familiar rhythms continue unchanged, but they now exist within a much larger context. Our planet moves through a layered, extended galactic structure that stretches far beyond what the eye can see. This expanded view doesn't make Earth less significant. If anything, it highlights how remarkable our situation really is. The solar system occupies a quiet region of the galaxy, far enough from the chaotic center to avoid disruption, positioned in a stable orbit that has persisted for billions of years. This cosmic real estate has allowed complex chemistry to develop, life to emerge, intelligence to evolve. The galaxy's true scale also reveals something about time itself. Light from distant stars in the halo has traveled for tens of thousands of years to reach us. When we look at these faint points of light, we're seeing the galaxy as it existed long before recorded history began. The view is always a mixture of past and present, a temporal layering that mirrors the physical structure of the Milky Way itself. Most of what shapes our galactic environment operates invisibly. Dark matter guides the motion of stars without revealing itself directly. The stellar halo influences the overall structure without contributing much visible light. Ancient merger events continue to affect the galaxy's evolution. Long after the original collisions ended, this hidden activity creates a kind of cosmic background stability that allows more familiar processes to unfold predictably. The Sun's position in the galactic disk means we experience regular passages through different environments. As we orbit, we sometimes move through spiral arms where star formation is active, sometimes through quieter regions between the arms. These changes happen slowly, over millions of years, but they can influence conditions in the solar system. Ice ages on Earth might be partly connected to these cosmic seasons. Our local stellar neighborhood contains dozens of nearby stars, but this density is unusual for the galaxy as a whole. Most of the Milky Way's volume is nearly empty space. Even in the disk where we live, typical distances between stars are measured in light years. In the halo, stars are separated by much greater distances. The universe is far more sparse than our relatively crowded corner suggests. Scientists continue to discover new streams of stars in the outer regions of the galaxy. Each one represents a story of cosmic archaeology, evidence of past events that shaped the Milky Way's evolution. Some streams are relatively fresh, created by ongoing tidal disruption of nearby dwarf galaxies. Others are ancient, their stars so scattered that only sophisticated computer analysis can reveal their common origin. The galaxy's rotation creates a kind of cosmic mixing. Stars born in different regions gradually spread throughout the disk over billions of years. The Sun itself has probably migrated from its original birthplace, carrying the entire solar system on a journey through different galactic neighborhoods. This slow churning helps distribute heavy elements created in stellar cores, seeding new regions with the materials necessary for planet formation. From Earth's surface, the night sky appears as a dome overhead, but this view represents only a thin slice through the galaxy's full three-dimensional structure. Most of the Milky Way lies hidden below the horizon at any given moment, or remains invisible due to dust and distance. We experience the galaxy edge-on, seeing it as that familiar band of light rather than the face-on spiral that appears in photographs of other galaxies. The expanded understanding of our galaxy's size doesn't require constant attention. It can exist as background knowledge, a quiet awareness that the environment surrounding Earth is deeper and more extensive than it appears. This knowledge doesn't change daily experience, but it can provide a sense of cosmic context that feels both humbling and reassuring. The Milky Way existed long before Earth formed and will continue long after current conditions change. This continuity creates a kind of temporal foundation beneath the shorter rhythms of planetary and biological time. Individual lives unfold within this larger framework, brief but meaningful episodes in an ongoing cosmic story. As awareness settles back toward more immediate surroundings, the galaxy's expanded scale can remain present without being overwhelming. The Earth continues its familiar motions. The sky maintains its recognizable patterns, but the mental map containing all of this becomes slightly larger, slightly deeper, with room for more mystery and more time than previously imagined.
you.